this resource, we should reserve biomass for better uses. For example, close the gaps, for instance, when the wind is not blowing or the sun is not shining, then we can use the biomass for that purpose, for providing electricity. On the other hand, we can consider biogas as a platform chemical which we can convert it to a number of high-value products. So you can see the anaerobic digestion here. You can see it as a treasure trunk where we can convert both the methane and also the CO2 to a number of different products. We can convert the methane to microbial protein. We can convert the methane to biomethane, the biogas to biomethane. We can produce plant growth promoters in the form of hydrogen oxidizing bacteria, methanol, aviation fuels, biodiesel, chemicals, algae, cultivate algae on the CO2, biodegradable plastic, osmolytes on methylotrophs which accumulate osmolytes. For example, ectoin, which is a very expensive product, biopolymers, for example, polyhydroxybutyrate. So you can see here, we have all these waste, we can transfer them to biogas through the anaerobic digestion process, and then from there we can go to a large number of different products. So this is the trend nowadays, and this is quite much what they are doing all over Europe nowadays. So I will mention that now we go beyond biogas. Through biogas, we can use biogas as a platform chemical in a way. So we have different concepts nowadays, integrating power to gas technologies. That means producing hydrogen, which can capture the CO2 and give more products, for instance, methanol. Syngas biomethanation, where we have pre-treat the woody biomass or the recalcitrant biomass to pyrolysis oils, and also syngas can be produced, and then we can combine biogas process with syngas fermentation. We can produce by syngas fermentation alcohols, chain elongation, biogas upgrading, single cell proteins, high-value products, platform chemicals, alcohols, bioplastics. So today I will focus in one of those processes, which is called biogas upgrading, or you can also call it biomethanation. So biogas is fed, biogas reactors are fed with organic waste, and biogas is produced while the effluent is digestate, which is used as fertilizer often. The biogas is consisting from 50 to 70% methane, while the rest is carbon dioxide. And as I said previously, it's typically used for electricity and heat production. However, if we remove the CO2 from the biogas and upgrade the methane in the biogas to over 95% methane, then we can find other uses of Europe, and you can see how many plants have biomethanation plants. For instance, in 18 in European countries, they have already biomethanation plants. In 2019, we had 725 biomethanation plants in Europe. That means plants which they upgrade their biogas to methane, 95 to 98 to 100% methane. So you can also see here in Denmark the number of biogas plants throughout the years up to 2020 for electricity production is stable. However, all the new plants actually they produce methane to put it in the gas grid, in the natural gas grid. So you can see all the increase, the development, the increase that have come the last years they have included methanation plants, biogas upgrading plants. And you can see here the number of biogas plants in Denmark is increasing throughout the years, but the biomethanation plants, which is this dotted line, has increased. The rate of increase is higher than the biogas, the new erected biogas plants. So the methods they use to upgrade the biogas nowadays, there are many commercial methods like wet water scrubber, pressure sweep absorption, amine scrubber, etc. All these methods, you see that they are very old methods and they used throughout. However, all these methods, they are not using the CO2. They actually throw it out in the atmosphere. They waste the CO2. We have developed a new method where CO2 is captured with hydrogen, together with hydrogen, through hydrogenotrophic methanogenesis throughout this reaction, by this reaction. That means hydrogen plus carbon dioxide is converted to methane. And this reaction is catalyzed by methanogenic archaea. So on the other hand, you can say we need hydrogen here. Where do we find the hydrogen for this process? The hydrogen can be obtained by electrolysis of water using surplus electricity from, for example, windmills or photovoltaics. So that means we can use wind mills when we don't need the electricity in times that we have wind, but we don't need the electricity to hydrolyze water, and then the hydrogen can be used to capture the carbon dioxide from the biogas to produce methane through this reaction. And you can see this process actually as integration of windmill energy with the biogas sector. So you can see it as the storage of the hydrogen, of the storage of the wind electricity or the photovoltaics when we don't need the electricity produced. And this you can say it's a second generation upgrading technology, because in this case we don't throw the CO2 out, but we capture it to make more methane. And you can do it in several ways. We have the wind here, we can produce electricity, hydrolyze water, and the hydrogen can go either directly in the biogas reactor to upgrade the biogas, or it can go to a separate reactor together with the biogas to upgrade the biogas. This direct method, of course, might seem more sustainable. On the other hand, this has an impact on the process, because by removing the endogenic carbon dioxide, the pH is rising drastically. So therefore, we can have also another option where we have a hybrid process. We can upgrade the biogas where we still can maintain the pH at levels that they are acceptable, and then we have a polishing in a separate reactor afterwards. We have been working with all these processes for many years, 5-6 years maybe, or even more nowadays, and we have attacked the problems and we have identified the problems that they are existing. So challenges for biogas upgrading, for the first is we need hydrogen. Hydrogen, if not, is not available as a residual renewable energy, then the process is not viable. For the second, the hydrogen provision is probably not continuously secured, because maybe we don't have residual extra electricity all the time. Another challenge is the gas-liquid transfer. That means we need to have the right configurations. The filling material of the reactors where we mobilize the biomass has to be selected carefully. The pressure, do we need pressure? We don't need pressure in the biogas in their upgrading reactor. Also, the microbiology can cause a challenge in this case. For instance, there is a competition between homocytogenesis, where hydrogen and carbon dioxide results to acetate rather than methane, and then methanogenesis. We have this competition, which sometimes we need to be able to steer to avoid acetate formation and get actually a methane instead. The pH increase is also a problem, especially in the in situ process, where we put the hydrogen directly in the biogas reactor, and that means by removing the endogenic CO2, we actually disturb our pH, which increases significantly. We should also remember that this process is exergonic, that means gives energy out, so we have to have some arrangements to take care that our reactor, upgrading reactor, is not overheated. These are some challenges we need to take care of when we upscaling. So this is the microbiology I mentioned, the problem. The hydrogen actually can go through hydrogenotrophic methanogenesis to give biogas methane, to give methane. However, the hydrogen carbon dioxide can go through homocytogenesis to give acetate, which of course can also go to biogas in case we have acetylclastic methanogens. But I mean, it's not always possible to be sure that the hydrogen carbon dioxide will go to methane. In some cases, it can end up as acetate. So we have been working for many years. We have identified and solved a lot of the problems, especially, for instance, to avoid the acetate formation. We need to provide the nutrients to the reactor, or also in cases that the process is not optimal, then it goes to acetate formation. We have we have conducted some experiments at pilot scale at the wastewater treatment plant, where we installed a pilot scale reactor to upgrade their biogas. Then we moved at the LNV biogas plant. It's a full-scale manure-based biogas plant, and we tested our trickling bed reactor. So you can see here it's Denmark. We are located here at the university, and then the LNV biogas plant is here, and we moved our pilot scale reactor to here where we tested it. So you can see here it's a pilot scale reactor. It's a trickling bed reactor, which is fed, the gases are fed from the bottom going up, and then we have trickling from the top with trickle nutrients, which is digestate from the effluent from the biogas reactor, we trickle down to provide nutrients for the process, while our gases for the biogas and the hydrogen are provided for the bottom, so they go up while the nutrients are trickling downwards. So we installed this reactor to the plant. You can see here it's in a container. You can see here the real pilot plant and the trickling bed reactor. Here are the pumps providing the digestate from the top, trickling downwards, while the gas is inserted through membranes, through diffusers from the bottom going up. And here it's the control system of the reactor, the PLC. You can see we have also some outlets here where we could take samples to measure, to see the microbiology of the system. So we measured both the attached growth on the foam. We had polyurethane foam as packing material. So we took samples to see which microorganisms are the different heights of the reactor. We also measured the microbiome in the liquid phase of the reactor to see how it was distributed. And also we, of course, measured the inoculum we used. The inoculum was basically digestate from a biogas reactor. So you can see here the operation. We operated it for 275 days approximately. And after the startup of the reactor, it went very fast to high methane percentage. So it was around over 90%. Here we changed the composition of the gas. So we turned it to stoichiometric. So that means that we reduced the hydrogen content here. We are added, so you can see slight fall in the process. So in this experiment, actually, we had two stops where we did not feed the reactor. So the P1 was a standby period where we did not feed the reactor because we wanted to simulate that we did not have hydrogen residual electricity. So we stopped. This is a hot standby period where we kept the reactor hot. Well, here we had the cold standby period where we stopped the reactor for this period here, almost a month, where actually we did not keep the reactor cold. You can see after that we were almost 90%. The production, of course, stopped because we did not feed hydrogen, and then soon after it went up. We had here 98% methane. At this point here, we doubled the flow of the reactor. We overloaded so we could start seeing homocytogenesis, and we found out that the diffusers were blocked, so we changed the diffusers here. So after we changed the diffusers, so we could see immediately increase of the process, and then we saw that it went back to very high methane content again. Then we had the cold stop period. After that, we again very fast we restarted the process, and here we had low methane content because we discovered that we had leakage of the hydrogen. So we didn't supply the hydrogen we were nominally thought we would supply. So after we fixed the leakage, then again, very fast, the methane went to 98.5%. And then here you can see a small drop again because we doubled again the rate. So we also measured the microbiology here. We took samples from the different levels, and we saw that at the bottom of the reactor, we had a very active methanogenesis, hydrogenotrophic methanogenesis. Also in the middle part, we make metabolic reconstruction of the metagenome assembled genomes we had. And also here at the top, we had a lot of assembled microorganisms, which were Clostridia, bacteria, and were actually creating also a kind of foaming of the reactor. So the learnings of the pilot scale operation from the deep biogas plant is that stoichiometric hydrogen supply will ensure high methane content. So this is very important because the cases where we saw leakages and so on, the methane content stopped. So we need to supply the hydrogen in order to capture the carbon dioxide. So this is of course very logical. The process is dynamic, changes very fast. When we stop and then restart, it starts fast. It's robust. We can stop it for several months without keeping it hot or without any maintenance, and then can fast reestablish after discontinuation for some time. The keeping temperature during non-operational is not crucial, as we saw. Too compact filling material or injection diffusers might result in insufficient contact of microorganisms to the gases. So we found actually that this polyurethane foam that we used was not that good because it was really compact and was not the best. So later on we found some other filling materials on PVC base which actually were more giving better contact between microbes and also the gas phase. Good microbial biofilm ensures good and robust operation. And we had almost complete upgrading, over 95%. Here are some papers we have published. And now we have a project with some commercial collaborators which are going to upscale the process. And we are going soon to have the first in the world biological biogas upgrading technology installed in full scale. So the socio-techno-economic assessment showed that the hydrogen price is the most crucial part of the economy of this process. So the biogas process is a scavenger. It's a very wide, broad application process. Future applications are going to be beyond electricity and heat, and the biological biogas upgrading is feasible as a power-to-X technology. And thank you very much for your for listening. Thank you very much.
We would like to thank Professor Irni Angeledaki for a brilliant talk. So if there are any questions, since it was a pre-recorded file, so we can take your questions and we can transfer it to Professor Angeledaki through email. So I don't think there is any question. So we will proceed, and our next speaker is Professor Samir Kumar Khanal. So he is present with us right now in Taiwan. So he'll be delivering a talk on nanobubble technology applications in algal production and aquaponics. So we would like to invite Professor Khanal to give his plenary talk on his topic. Over to you, Professor. Thank you.
Hello. Thank you sir, so much for introduction, and a very good morning to all of you. Perhaps good afternoon and good evening to the other part of the world. And I also like to thank the organizing committee, especially Professor Chongdi Dong, Professor Ashok Pandey, and then Anil, and also Rita Raishangani for organizing this conference and inviting me to give this talk. So my presentation here is focusing on the nanobubble technology applications in algal cultivation and also in agricultural aquaponics. So now before I go further, I would like to give you some little bit about Hawaii. So Hawaii is a wonderful place. It's a very touristic destination. And this is, people just come there to enjoy the beautiful beaches. So if you have a time, visit our island and enjoy the beaches. This is also a nice place for hiking. I do a lot of hiking in the mountain. It's not only beach, but they also have a lot of beautiful mountains for hiking. It's a very, very good place to hike around. The one you're seeing here is actually a very nice place for snorkeling. And you can actually, these are formed by the volcanic eruption. It's a conservation area. They are limited how many people can go there. So they restrict the people. So they conserve it for tourists to go there. Yeah. So with that, let's go to today's topic. So why this nanobubble is so important? So if you look at the biological wastewater treatment processes, one of the very important consideration is actually supplying enough oxygen for removing organic matters, removing nutrient, and also for other type of organic matters or micropollutant. In many of those processes, we use what we call diffuser or sometimes surface aerator to supply the oxygen needed for the degradation of organic matter or nutrient removal. And the cost of aeration for these biological processes are enormous. Sometimes it costs about 75% of the total operating cost. And many of those surface aerator or mechanical aerator or diffuser, the transfer efficiency for oxygen is not more than 10%. So in fact, a lot of the air just escape to the atmosphere without getting to the microorganisms that are doing the job. From that perspective, supplying efficiently oxygen in the biological system is one of the very important to improve the efficiency of the systems. Now, if you look at the agriculture, which is a very important for food production, food security, in also agriculture, we have to maintain a good amount of oxygen in the rhizosphere zone, in the soil zone. If there is a limited oxygen, it gives you a condition where it can cause a lot of diseases in the plants, especially root rot disease, poor nutrient utilization efficiency, and then at the same time you may have a less yield from the plant. So that is one of the challenges in the agriculture food production. And also, if you look at the intensive agriculture, especially using some of the hydroponic system, it's very important to maintain enough oxygen in the system. Otherwise, you may have a problem of anoxic conditions and a lot of other issue in the plant. So that's why it's quite important to supply oxygen from this side. So if you, from that perspective, the nanobubble play a very important role. Now, if you look at the nanobubble, some of the gases which are not easily soluble in the liquid phase, such as oxygen, carbon dioxide, hydrogen, carbon monoxide, maybe sometimes carbon dioxide, they cannot be easily dissolved in the liquid phase. So if you have that problem, then it may affect many of the microbial or bioprocesses. If you look at here example, this is just one of the bioreactor. You can see very high concentration of microorganisms in the system. And if you are running aerobically, you cannot actually supply oxygen enough for this microbial population to actually sustain. So that become a rate limiting steps, how much product you can produce. So in that case, you have to either do intense mixing or you have to find other way of supplying oxygen. So in that sense, if you have a nanobubble aeration or nanobubble oxygenation, you actually can supply enough oxygen for large quantity of microbial population in the system. And at the same time, you can also use this nanobubble for producing microalgae or macroalgae, especially supplying carbon dioxide in the form of nanobubble. And you can also use this nanobubble in anaerobic digestion for many applications, which I'm going to talk to you later a little bit more detail. So if you look at some of the applications of nanobubble, you can see here, you can use air nanobubble for improving the crop yield in agriculture. You can also use this one for producing biomass for protein production and other application, or even for producing other type of metabolites which are aerobically produced. You can also use nanobubble, ozone nanobubble, especially for water reclamation, reuse, disinfection. They're very effective. You can just supply a small amount of ozone nanobubble. You can also use CO2 as nanobubble, very small bubble, and you can have a better oxygen CO2 transfer in the liquid phase and improving the yield of macroalgae, microalgae, and metabolites as well. So there's other thing that I'm going to talk to you a little bit more. You can also use hydrogen is not very easily soluble in the liquid phase. You can supply hydrogen as a nanobubble and improve the biogas upgrading, especially just now you listened to talk by Irene who discussed about biogas upgrading. You can actually supply hydrogen as a nanobubble and combined with the CO2, and you have hydrotropic methanogenesis with a very high concentration of methane in the gas phase, 98%. And you can also use carbon monoxide nanobubble for syngas fermentation. And actually there's other research, they're looking at methane nanobubble. So you can actually use, methane is also not very soluble in the liquid phase. So if you want to supply nanobubble in the form of methane nanobubble, then you can actually produce many of the metabolites consumed by the group of microorganisms which are autotrophic. They use methane as their carbon source, energy source, and converting this methane by the methanotropes into single cell protein, bioplastics, and also different organic acid and ectonic acid. So these are essentially produced from methane. So there is a lot of potential of using nanobubble for different applications. So now, if you look at the publication before 2016, they defined nanobubble as the gas pill bubble with the size of about 1 micrometer or 1,000 nanometer. So that is the original old definition of nanobubble. Then since there was a different classification, different definitions, they set up a ISO standard to have a very uniform definitions of the bubble size. And they developed this ISO standard for these fine bubble associations. And they now actually replaced nanobubble with ultrafine bubble. So they don't actually say very often nanobubble, they say ultrafine bubble. And that is essentially the definition by these fine bubble associations. Now, these nanobubbles, as you can see here, these are the gaseous cavities. So they are the gaseous cavities in the aqueous phase, in the liquid phase, and their diameter could be somewhere ranging from 50 to 200 nanometer, very, very small. If you look at the coarse bubble, it could be a few millimeter size, but you can see these nanobubbles are 50 to 200 nanometer size. And these nanobubbles are formed by different methods, which I'm not going to go in detail, that can be formed by hydrodynamic cavitation. Or you can also use some type of ceramic membranes. They have a small pore. You force the gas to pass through this membrane at a certain pressure, comes out as this fine bubble or nanobubble. So there's also a way of producing nanobubble. The different techniques are there. So if you look at the literature, before 2000, there was less acceptance of the people. They didn't know really what is nanobubble because there was no way to identify and characterize nanobubble. But only after 2000, the first image of nanobubble came out by the measurement using the atomic force microscopy. So that is essentially the way they measure the size of the nanobubble. And after that, now you can see a significant amount of research and development in the field of nanobubble technology for different applications. So if you look at some of the important properties of nanobubble, they behave like a colloidal matter. So that means they have a surface charge. These are negative surface charge, very similar to colloidal particles or bacteria. So for negative surface charge, and then also they have the high negative zeta potential. So that means they are very stable in the liquid phase. When you have high zeta potential, negative zeta potential, these two particles, they don't come closer. They stay in the stable condition in the liquid phase. And then at the same time, because of smaller size, they have a better mass transfer efficiency, and they are in the liquid phase for a long time. They don't escape to the head space. They will stay in the liquid phase for a long time. So that is some of the properties of this nanobubble. So if you look at some of the mass transfer equations, we use what you call two-film theory, and which is very common. You can see on your right side the concentration of the gas in the head space. Then to go into liquid phase, it has to overcome resistance. One is the resistance on the gas film side. Then you go to interface, then sudden drop in the interface, and after that it enters into the liquid film, and then it goes into the liquid phase. So you can see these are the resistance that any of the gas molecule has to overcome to get into the liquid phase. Now this depends on many factors, how fast the gas molecule can dissolve in the liquid phase. That depends on the concentration of the gas molecule in the head space, the size, the surface area, temperature, and so forth. And one of the most important factors is actually the concentration gradient, the concentration difference between the the liquid phase, gas phase, and the liquid phase. Now by using nanobubble, you can maintain very high concentration of this gas in the liquid phase, thus maintaining a very big difference between the concentration gradient that allow the rate of reaction to go much faster. So if you look at the basic theory of the mass transfer, you can see a big size bubble, macro bubble. This macro bubble, you can see how much oxygen can be around. If you have a big one, you can just have few of those. But if you break this big bubble into a smaller, tiny bubble, the same bubble can hold many oxygen molecule or CO2 molecule or any gas molecule. So by having a smaller molecule, you have a much larger surface area, and thus you can have more oxygen or more gas in the liquid phase. That means you can actually maintain much higher concentration of those gas molecule around this bubble, and that will diffuse into the microbial cells. Okay, so that is the basic mechanism by which the nanobubble actually moves from the gas to the liquid phase, from liquid phase to the microbial cell or biofilm or so forth. So that is the basic. So you have a smaller size, large surface area per unit volume, thus allow the much effective transfer into the gas phase. Now we also did some study looking at the mass transfer rate, which is a very important, how fast the molecule transfer from gas phase to liquid phase. If you look at this plot, top one is nanobubble mass transfer rate for the oxygen, and bottom one is actually the conventional diffuser, simple diffuser. Your mass transfer rate using nanobubble is almost 4 to 5 times higher. That means they go much faster than simple diffuser. At the same time, you can actually maintain much higher concentration, supersaturated. Saturation concentration goes beyond 100%. Compared to, you can see in the top one, which is your nanobubble, the bottom one is a conventional diffuser. And they can maintain much higher dissolved oxygen concentration in the liquid phase compared to the normal aeration. So that means you can maintain much higher concentration. So these are some of the merits of this nanobubble. Now look at the colloidal chemistry or colloidal theory. They have a surface charge. The surface charge gives you a zeta potential. So zeta potential essentially means you have the stability of this particle in the liquid phase. And because of this surface charge, and because of this high stability in the liquid phase, and then their interface, electrostatic interaction, this property can be harnessed for many applications. Some of the applications including membrane defouling. If you have a fouling in some of the membrane processes, nanobubble has a potential to minimize the fouling of the membrane surface because of this interface interactions, electrostatic interactions. It can also be used for dissolved air flotation, for removing some of the final particles that cannot be removed by simple diffuser. So there is other benefit. And of course, it can also enhance the transfer of cations because of the negative charge. It can actually attack positive charge, allow the positive charge to easily diffuse in the cells, plant cell and other type of cell where you require some of the cations. We also did some other characterization studies. If you look at this plot, you can see how the pH affects the zeta potential and also the concentration of the bubble in the liquid phase. The concentration of the bubble actually did not change with change in the pH. They remain fairly constant here. You can see somewhere in the range of 100 million of the bubble per ml of the liquid. Zeta potential certainly changes with the pH. As the pH increases, zeta potential also increases, which is very common. We also look at how the size of the bubble changes with the pH. You can see this size was not affected by the pH. No matter what your pH, size remains fairly stable. Here we saw in the range of slightly lower than 100 nanometer. So pH did not have any effect on the size, but of course it has effect on the zeta potential. So that's one of the common theory. If you look at you have to measure nanobubble, and it is not easy to measure nanobubble. It's a nanoparticle, and we use what they call the nanosite, developed by the Malvern, which is commonly used. One of the drawbacks is that it actually covers all the nanoparticles, not only nanobubble. So we have to really be very cautious about reporting these values. So here we have this nanosite machine that we purchased here to measure the nanobubble. There are two figures you can see. One is the control, that is the milky water. Second one is the nanobubble water. You can see when you pass this nanobubble from this nanosite, you can see those bubbles moving. They capture the image and give you the size and concentration of this bubble. Sometimes if you have a nanoparticle in the water, they also capture that image. So sometimes we have to look at the background concentration also. That's very important. So this is also other part, to look at the zeta potential stability. So we measure zeta potential in this case. And you can see that with the time of aeration, our zeta potential remain fairly stable after 40 minutes of aeration. It's about minus 27 millivolts. So that means pretty stable particles. We also look at the size of the particles. So if you aerate it, within 10 minutes, the size become really stable in the range of 120, 130 nanometer. So that's pretty stable size. So after 10 minutes of you are nanobubbling the liquid, your size is very stable. It doesn't change significantly. So you can say you can produce nanobubble stably in the liquid phase. And we also look at, in the fully saturated solution, it may take somewhere about 40 to 50 minute time. And you can say concentration of the nanobubble in the liquid, maybe you can see here about 200 million to 30 million nanobubble per ml. So that's the concentration of nanobubble. If you look at the basic concept, nanobubble, when you generate nanobubble, it contains a different size of the particle, nanobubbles. Some could be micro, some could be mega, some could be nano. So it essentially gives you some kind of distribution curves. And in the range of this one, in the nanobubble range, your particle could be somewhere 200 to 300 million per ml. So that's the concentration of the nanobubble. You don't get 100% nanobubble because that's impossible. So you have a distribution of those nanobubble. We also look at this, again, control and and then the nanobubble air, oxygen nanobubble. So we can actually take the image and see the different size of this nanobubble through this nanosite unit. Okay. Now this also gives you the characterization, more characterization. If you look at this one, as I mentioned to you that when you measure nanobubble, it not only give you the nanobubble, it also measures nanoparticles. So you have to be careful that when you measure, you have to see the background concentration. It doesn't give you all nanobubble because there could be a lot of nanoparticles. It measures nanoparticles. So you can see on your left side, you have the control. Control also contain nanoparticle because of the different type of particle in the water. And on your right side is actually the nanobubble water. So you can still see there is a nanobubble and nanoparticle. And we also look at the same for carbon dioxide, which is very important for macro and micro algae production. And we also characterize, and we can see they have concentration goes up to 100. If you look at this size of 100 nanometer to 150 nanometer up to 100 million of the nanobubble per ml of the liquid. So you can actually get a lot of those nanobubble CO2 in the liquid phase. So you can see this is the image of the nanobubble CO2 that is coming from the nanosite unit. And this is again measuring the background concentration. Very important to see how the background concentration goes. So you still have the background concentration of nanoparticle, and we can also characterize the nanobubble of CO2 in the liquid phase. Now, other important property of nanobubble is that they have, they can actually produce reactive oxygen species. When you produce nanobubble, it's a cavitation process. So that means you have a very strong shear force acting there. And the shear force essentially causes breaking down of the water molecule and producing hydroxyl radical and many other type of reactive oxygen species. And these have a lot of application, especially for degrading some of the organic pollutant, micropollutant, and then also it can be useful for seed germination. It provides a better seed germination using nanobubble. So how we produce nanobubble? There are different techniques, as I mentioned. One of the very common way in the liquid phase is by the cavitation. So essentially, it's a venturi tube. You allow the liquid to pass through this narrow tube, and you inject the gaseous molecule at high pressure at that on the top. And as the liquid and the gas escapes, the pressure drops suddenly, decompression. And decompression causes atomization of the particle, giving rise to a nanobubble. And that is a very commonly used method of producing nanobubble in the liquid phase. You can also find the same in the nature. You can produce nanobubble as well. But other technique is, of course, you can also use membrane. So there are different membranes that are actually being developed to produce nanobubble of different size. And sometimes what happens that when you produce nanobubble from membrane, the membrane surface sometimes is hydrophilic. So that means the bubble cannot escape very easily. So you have to modify the surface to make a little bit hydrophobic and maybe some pressure, allowing pressure to pass in a cross-flow direction, and then getting those nanobubble out from the surface. So there's also other way of producing nanobubble using membrane, which is quite common for commercial application. So this is essentially the setup showing the nanobubble generator unit that produces nanobubble in the liquid phase here, and then we collect the nanobubble. Slightly milky color because of the different size that it produces. That is the nanobubble coming out from the liquid phase. Now application comes here. You can see they have many different applications. So it's a nanobubble with 1 million of applications, and many of them are still evolving. We really don't see many of the fundamental work. So there are a lot of different potential of nanobubble is coming up now, including I have pointed out some of those here. It can be used for many of the biological processes, bioprocessing, organic removal, and then also agricultural applications, membrane defouling, and macroalgae production system, as well as seed germination and degradation of some of the refractory compound. Many others. There are a lot of benefit that comes. So I'm not going to go in detail. So I'm going to share some of the work that we actually have done on using nanobubble for aquaponic, hydroponic, or bioponic applications. So we want to see that how nanobubble affects the fish growth and plant growth in hydroponic system. If you go to market, many of the product you see now is actually grown hydroponically, because you can grow much higher amount, control environment, less attack from insect and pesticide and many things. So there are a lot of farming, organic farming are actually grown hydroponically or aquaponically or bioponically. So this is one of the studies that we conducted for a few years. And if you look at the fish itself, fish uses protein-rich diet, and they only consume maybe 15 to 20% of the diet per body mass. And about say 70% of the nitrogen actually become waste. A lot of nitrogen comes out from aquaculture system as a waste. It can be released from their gills in the form of pre-ammonia or ammonia in the liquid phase, or it can also be coming out in their solid waste in the form of feces. And these all contain nitrogen compound. And these nitrogen compound are essentially going through a process of nitrification, converting ammonia into nitrite and nitrate. After nitrate, then if you don't have oxygen, it goes into denitrification and you lost nitrogen. But if you want to capture nitrate, then nitrate can be used to produce plant growth, and that is essentially used for edible plants, growing different type of vegetable and so forth. So here, our goal is essentially improving the nitrate production and using nitrate for growing the plants. So this is the setup that we have shown here. You have the tank where we grow some fish, and then you have the grow bed, the green one, where you grow plants, lettuce, pak choi, you name it. Many type of plant can be grown hydroponically, tomatoes and so forth. So this is essentially the showing you the concentration of the nanobubble with the different size. And you can see here, size was about less than 100 nanometer. So 90 nanometer was the normal average size. And if you count the area itself of the particle, you can see they have about maybe 154 million of this particle in 1 ml of the liquid. So that is the amount of particle. This was done almost 5 trials data. We look at the fish yield. With the nanobubble water, your fish growth was actually maybe 15 to 20% higher yield of the fish can be grown. That means you actually get better yield of the fish because of improved water quality and higher oxygen level in the liquid phase. So that is one on the fish side. But very interesting finding was on the plant side, which was very unexpected. If you look at these two type of letters, one is the normal aeration, normal diffuser on your left side. On the right side, if you look at, that is actually nanobubble water. So you are bubbling the air using nanobubble and applying those into these tank, 2 different setup. And on the right side, you can see the root growth is very intense and very clear when you have nanobubble. On the other hand, when you have normal aeration, root growth was not very prominent. They are all under the same condition, supplying same amount of air, but one nanobubble, one normal diffuser. And if you look at the plant itself, there are 2 setups. If you look at this one, left side is the normal aeration, and the other one on the left side is actually the nanobubble. The right side is the normal aeration. In the normal aeration part, the plant was a little bit fluffy type, But if you look at the nanobubble, the plant look is small, but it was very compact. And because of the compactness, your mass was much higher. And very interestingly, if you look at the mass growth, you are actually getting almost 2 times higher yield with the nanobubble water compared to normal air. And after 2 weeks to 3 weeks time, you can see there is significant difference between the normal aerated water and the nanobubble aerated water, because the plant growth is not linear. They grow slowly. After some time, the root grows faster. They take up more nutrient and they grow much faster. So that trend you can see as the plant started to mature, it takes up a lot of nutrient, and then the plant shows significant higher yield. So by nanobubble aeration, you can actually achieve almost 35 to 45% higher yield of the biomass. So that is the benefit of using nanobubble. Now we also look at the nano CO2, now not air, we are using the CO2 as a nanobubble. Now I really don't know if it is because of the concentration of CO2 or because of size of the bubble. Remember, normal CO2 you are supplying as the macro bubble, but here you're supplying nano bubble CO2, small size. Now in this plot you can see clearly one is normal CO2, no, there is just no nanobubble, normal CO2. The second one, we supply CO2 as a nanobubble. The algae growth, you can see they have much greener color, much higher OD compared to the other one. And we could actually see yield growth was in this, with nano CO2, you can see actually up to almost 1.4 times higher yield just for a couple of trials. So you can see with nano bubble CO2, you're actually getting a higher yield of those algae. And that is one of the benefit of using nano CO2. Now there are different mechanisms involved. It could be because of higher solubility. It could be other properties of the nanobubble, including size itself. So a lot of things need to be carried out. But you can see there is a difference in terms of the yield of the nanobubble CO2 and normal CO2. And that can be something expanded in larger scale. Other thing you may also notice that when you supply nanobubble CO2, so when you grow algae, your pH will drop rapidly, right? Your pH will essentially increase because it takes up CO2. pH will continue to increase. But when you supply nanobubble CO2, you actually can reduce pH. So there's a pH modulation effect taking place. Algae is consuming CO2, your pH is going to increase rapidly. But at the same time, when you supply this CO2 as nanobubble, you increase solubility, and your pH will actually be lowering. So you have some pH modulation effect taking place without adding any chemical. So there is something that you can actually do some process control and modulate pH fluctuation by supplying nanobubble CO2 instead of adding other type of chemical to maintain the normal pH. So that is something could be very helpful to actually modulate the pH in this pH system into the algae system. That is for the macro algae, but you can also use them for macro algae and other applications. So there's a lot of potential of using this. And you can also use nanobubble CO2 oxygen for dark fermentation also, because there are some algae that can grow in dark fermentation condition. You can also use that condition. So there's a lot of potential of this application. Now, just want to summarize the overall concept here. So nanobubble provides an opportunity for dissolving some of those gases that are not easily soluble in the liquid phase because of their poor solubility, especially if you want to grow plants hydroponically or bioponically. You can actually get almost 50% higher yield with using nanobubble aeration. And also it shows a better nitrification, a better higher nitrate yield with the nanobubble water. And there's a lot of potential of using this technology for different applications. I pointed out some, but not all. Having said that, this is not a panacea. There's a lot of challenges still forthcoming, including applications in the large scale. We also don't know a lot of mechanism how nanobubble actually enhance the plant yield, whether it's because of solubility or because of the different physical and chemical properties the nanobubble has. There is something, not more fundamental research need to be done in this area. And also more studies are needed in terms of their full scale of commercial viability. What is the cost involved? How much it costs to produce this nanobubble generator? Of course, a lot of research are looking at producing this generator at a low cost, which is coming up. And last but not the least is a techno-economic analysis for cost effectiveness in the full scale application and so forth. So with this one, I would like to thank my funding agency as well as my students here who actually work in this project. And I will be happy to answer any question you have. Thank you.
Thank you so much, Professor Kanal. for such a thought-provoking presentation. And from your talk, I can say that nanobubble technology has many applications, especially in the agricultural and fish farming, and it may potentially help for sustainable development and economic development. Thank you, Professor Kanal, for such a good talk. And if there is any question from the audience.
Yes.
I'm just curious about one thing. So you talk about the stability of the nanobubble in the different pH, right? But for the real application, I think we can concern the other look like temperature effect. Have you consider about that? Yeah, temperature. Yeah.
As you know, solubility of any gas depends on temperature. As the temperature increases, solubility decreases, and vice versa. So in many of the application here, our temperature is about 25 degrees centigrade. So that's normal temperature we usually use. Yeah. Certainly, if you are looking at the higher temperature, then solubility of any gas will be lower. But in this particular case, nanobubble will stay in the liquid phase for a longer time in spite of the temperature. So that's one of the benefit of the nanobubble because of their higher stability. But we have not looked at the temperature itself, so that is something can be done, yeah.
So for most of the case, you perform, conduct the experiment under the closed system or the open system? Yeah.
Mostly open system.
Open
So
system.
it's a greenhouse open system. We don't close it, yeah.
Oh, really? Yeah. Thank you. Yeah.
Thank you so much. It was a really exciting talk, and I was waiting for this talk since long because I could not attend last time from BRSIA as well. So yeah, I just wanted to know whether we can use these nanobubbles in any aerobic bioprocesses, right?
Yes.
It should. So yeah, I really wanted to use it for bacterial cellulose production, in which we are working as well. So I was wondering how long we can, we do not have any system at present here to generate nanobubbles. So if we get some from somewhere, nanobubbled water, like oxygen nanobubbled water, can we use it for our this bacterial cellulose production? And also how long it can stay? Because if we think that maybe for 4 days, if this thing is going on fermentation, because I believe that these nanobubbles can stay longer, and the problem is even if we supply oxygen, so it just goes off on the surface and it goes off. So if it can stay there for longer time, maybe we get higher yield. So yeah, how long we can use it? And also one problem is we cannot sterilize it, right? Because we have to add it. So can we believe that it is sterilized water after generating nanobubbles?
Thank you, Rita, for wonderful questions. Let me give you a basic some physics. If I have a water in this bottle, just because I'm an engineer, I want to talk to you. If I have a water in this bottle, and I completely fill with oxygen or CO2, seal it completely, and if sealed completely, the CO2 oxygen will remain here forever, because that's a basic concept of the mass transfer. So as long as your head space is completely sealed off, and your nanobubble is here in the liquid phase, completely sealed, nanobubble or any bubble will remain there because there's no way they can escape. So that's a basic kind of physics of the solubility. Now, in terms of the nanobubble, certainly as the microbial cell, other processes consumes, the concentration go down because that's how it happens. But in terms of the stability, sometimes they can stay weeks, from days to weeks in the system because they are colloidal particle. So they stay much longer in the liquid phase. So that is one of the benefit of their long stability. Now, let me give you a few examples. You can use this nanobubble, completely seal in any container, and use that container for growing your system because you are sealing completely. And if you seal it completely, there is no any kind of head space open, then they will stay there for as long as the microbes will consume it. So that's the basic concept. Now, nanobubble itself, will not sterilize. You have to sterilize all your tubing, piping, everything, and then you can probably maintain sterilized condition. So we also have a problem when you grow microalgae. We sterilize everything because you don't want to have other type of microbes coming into the system. So yeah, nanobubble itself will not sterilize the system. We have to sterilize the system. And there are two ways you can generate nanobubble. One, you can use hydrodynamic cavitation in the liquid phase, or you can use some membrane technique to produce nanobubble as well. So there are two techniques that can be used. But also, I want to alert you that when you have nanobubbles, some of the nanobubble have been found to affect fish. So there are some studies, you have the nanobubble in the air, you also produce nanobubble nitrogen and nanobubble oxygen, because it's at 78% is nitrogen and 21% is oxygen. So when you produce nanobubble from air, you also have a nanobubble nitrogen that goes into the fish body, and the fish will die because of they call nanobubble disease. So sometimes we have to be careful that nanobubble nitrogen can also have some negative effect on the fish. But we have not seen such effect in the microbial. That is also something we can look at, how the nanobubble affects the microbial growth in terms of the yield, in terms of productivity. Sometimes maybe it may have positive effect. You may have less concentration but highly active microbial community if you want to produce some metabolite. So there's a lot of things that can be done in the system.
Thank you so much. It was really thought-provoking. And then I'll catch you later because I have so many other questions
No
as well.
problem. Yes, sure. Yes.
Okay.
Hello, Professor. I have a question. What is the pressure difference between conventional bubbling and nano bubbles?
If you produce a nanobubble from the hydrodynamic cavitation, it's the atmospheric pressure. So we essentially produce under atmospheric pressure. But if you are using membrane processes like ceramic membrane, we go pressure of somewhere 30 to 40 psi, okay, which is very high, 30 to 40 psi. So 14.9 psi is 1 atmosphere. Now it's about 14.7 is 1 psi. So if you want to produce nanobubble in the membrane, it may go up to 40 to 50 psi. So that means 3 or 4 times atmospheric pressure if you produce by membrane. No, because it will just come out and goes into the liquid cell, and it diffuses very slowly. So it doesn't produce a shear stress itself. That's a benefit, because if you do a lot of mixing, you have a lot of shear force taking place. But nanobubble diffuses slowly, so it doesn't actually provide you too much shear, so cell will not be affected by the shear stress, shear force.
Thank you so much, Professor. Since we are running short of time, so we'll like to thank you so much for your such a good presentation. Thank you, Professor. Thank you.
Thank you so much. Yeah.
Next, we have the next invited lecture in session C is IL9, Dr. Vijay Kumar Gupta from UK. He will be talking on evaluation of bioprocess parameters for pilot scale fermentative biohydrogen production using organic waste, economical challenges and future solution. So we will be going to that.
So we have his pre-recorded file, so we will play it now.
Good morning, everyone. Myself, Dr. Vijay Kumar Gupta from Biorefining Advanced Material Research Center of SRUC UK. Most of my work in past few years is focused on energy side on fermentative biohydrogen process production using organic waste, different range of bio-based feedstocks. So within Center for Safe and Improved Food and Biorefining Advanced Material Research Center, my key goal is to develop high value added products and innovative processes from biomass and waste feedstocks in application for applications in different industrial sectors. So here is we address key challenges like why waste recovery matters, sustainable use of resources, green technologies for value-added extraction and production from waste and recycling back to the process value chain in using circular economy platform towards zero waste concept. Applications of bio-based products in agri-food and pharma energy sectors and their roles in commercialization. So all in all, it's more about valorization of biomass to value-added product using circular biorefinery approaches, bioeconomy and biorefinery approaches. So having said that, in past 15 years, we are focusing on biochemical profiling, biocomposition analysis of range of different substrates that includes agri residues, office food, municipal solid waste, forestry waste, marine waste, including dairy waste, whey waste, green waste, kitchen waste, fruit and vegetable waste. In terms of why valorization of organic waste matters, as you can see here, it's a report from FAO 2013 that food waste alone contributes around 16% of total food wastage. It has been reported that about 20 million metric tons of waste were generated from 33 metric tons of processed oranges alone. Most of this waste goes to landfills, which creates enormous environmental pollution and hazards. Even the report from for 2012, which tells us that around annual worldwide food and vegetable waste wastage is around 45%. Because these are rich in cellulose, and these cellulosic waste have low lignin content, and their vast abundance make them a cheap source of production of valuable products like biofuels, biochemicals, and value-added energy outputs, for example, biohydrogen, biobutanol, syngases. Then here comes the why biohydrogen. As you know, hydrogen production has two main routes: thermochemical, which is more about pyrolysis and gasification; biochemical, which is more about biological hydrogen production, dark fermentation, photofermentation, sequential co-culture, photolysis, and biocatalyzed electrolysis of water. There are certain limitations of thermochemical process, which include product is having mixed with other gases. Thus, we need elaborate purification is required. Also, it needs of gas conditioning and tar removal. There are another main issues with thermochemical conversion is occurrence of catalytic deactivations. Also, carbon dioxide absorption, drying and chilling, membrane separation is a big issue in thermochemical biohydrogen production process. In case of hydrogen production process through biological route, which to me is cleanest, renewable, potential way to sustainable energy generation, the production of hydrogen via dark and photofermentation are considered to be more suitable and biochemical approach for over the numerous existing biological modes. Nevertheless, both biological route has certain limitations which we are trying to overcome with our recent technological development, which we are coming across with different another slides. Therefore, our present research is focused on an assessment and feasibility of integrated biohydrogen production strategy by combining dark and photofermentation as an advanced biochemical process while using organics biomass to improve the accelerated biohydrogen production process. So for pilot scale and industrial scale applications point of view, the focus should be given selection of both types of fermentative microorganisms, which we are also addressing in our current research by developing microbial consortia, enriched microbial consortia, I would say, for higher or improved biohydrogen production. We are also trying to develop surface engineer microbial cell factories which in turns almost in our current rate, almost twofold to threefold increase in biohydrogen production process in our country. Soon it will be submitting in one of the good channels, so you'll find more details on it. In terms of mechanism of dark fermentation biohydrogen, as we know, biohydrogen has certain benefits, which is eco-friendly, less energy intensive, greener technology, operation of operational and ambient temperature, atmospheric pressure, fossil co-products from different effluents. But there are key challenges, which of course related to the pass-fill mechanism of production of biohydrogen through photofermentation or through dark fermentation. Take an example of dark fermentation, where key challenges are selection of high-yielding microbial cell factories, which we are trying to overcome with developing recently developed surface engineered cell factories, where we have been progressed well, and we are getting almost twofold to threefold increase, as I said before, in biohydrogen production process. We are also designing how this cell factories, engineered cell factories, are gone up to the level of pilot plant. In terms of the fermentation biohydrogen pathway, which is very much dependent on in microbes responsible for. In all, over process, if you are using this just in microbial cell factory, which is optimized or being considered as a first step to produce this through dark fermentation, we notice that microorganism pyruvate formylase pathway was not able to utilize NADH, which is the key for hydrogen generation, resulting theoretical value 2 mole of hydrogen per mole of glucose. But acetate pathway gives a lot more results, which is 4 mole of hydrogen per mole of glucose released. In our surface engineered cell factory, they are more capable of addressing this issue in terms of producing a lot more hydrogen than we have getting in our current researches. In terms of the role of the role of nanomaterials in biological hydrogen production processes, we are also developing and working on how we can improve the overall mechanism of action of starting from pretreatment, enzymatic improved enzyme productions or biohydrogen production through the use of or presence of nanomaterials. In this reference, of course, the cost involved is the major factor for biohydrogen production, but we are focusing on developing more and more greener route for production of biohydrogen, production of nanoparticles, and then using of those nanoparticles for biohydrogen. The role of we have already analyzed the role of nanomaterials or nanoparticles in biological hydrogen production process through different routes in dark fermentation, photofermentation, integrated hydrogen production, and biophotolysis. That not only does improve production rate, it also include the yield, microbial growth, microbial metabolism. As we said, we are developing surface engineered cell factories, microbial sustainability in stress conditions, enzyme stability and durability, and also efficient production conversion rates. So this is more about how and in terms of feasibility of production of greener route versus chemical route of nanometal production and subsequent uses for biohydrogen production process. So in this reference, cost was involved in synthesis of nanomaterial may further reduce the cost of economy of the overall process when nanomaterial synthesis by green route as implemented in our current researches compared to nanomaterial synthesis by chemical route. Of course, and there are chemical and green synthesis method have their own limitations, which are matter of consideration. Nevertheless, it is anticipated that implementation of nanoparticles in cellulosic biohydrogen production process may overcome the existing limitations for production. This is one of our paper recently we published on synthesis of cobalt, nickel cobalt nanoparticles in application of single-state biohydrogen. Then again, this is one of the sketch of presentation of application of nanomaterials at every stage of the cellulosic biohydrogen production for enhancement at pilot scale. Various aspects of nanomaterials in overall processes of biomass to biohydrogen production, which include A, catalytic role of nanomaterial for pretreatment of biomass to remove lignin. B, nanomaterials mediated improved production of enzymes. C, nanomaterial assisted pH and thermal stability of enzyme. D, nanomaterial assisted enzymatic hydrolysis of biomass and catalytic role of in biomass. And E is more about catalytic role of nanomaterials on biohydrogen production through dark fermentation using sugar hydrolysates. So we are progressing very well on this. There is one of the example, the papers we published where iron nanomaterials using waste pulp of cesium cumene and its application and stability of one of the microbial cellulases. So it was more about the biochemical side, biochemistry side, but we did more in-depth characterization of proteins or enzyme engineering or protein engineering, molecular or cytotomics level, which is why and how it gets higher enzyme activity, high enzyme, let's say, protein. So we realized we did quite a different substrate and find out the best inducer media for enzyme and high-risk enzyme production, higher extracellular protein production, which is related to direct enzyme activities, and where this nanomaterial mediated enzyme production enzymes are why they are highly active. So when we did the transcriptome analysis, we did notice that nanomaterial mediated enzymes, they are having a lot more different active proteins compared to the control one, as you can see here. And when we did some, let's say, modeling and some comparison, we found they also have a soilin-like protein produced in their system, nanomaterial mediated culture. This is a kind of accessory protein helping the process and helping the cellulase for higher, for efficient biohydrolysis. Here comes, we have some of the papers we publish in efficient or enhanced enzymatic hydrolysis for, let's say, using wheat bran and then engineered cell factories. Then there are some results from our recent research, which is more about residual algal solid state fermentation for cellulose production under the influence of nickel ferrite particles. So you can see here, we saw the influence of nickel ferrite nanoparticles on crude cellulase enzyme production under the different concentration of fungal strains. Using one of our fungal strains, different concentration of substrate using one of our fungal strains. Here we use cyanobacterial culture as a substrate for solid state fermentation. So figure 1A is about increasing pattern in filter paper activity in presence of 1.5% of nickel ferrite nanoparticle with substrate concentration of 6 gram. When the 6 gram of condition was optimized, the substrate concentration we use an increase. 1B is more about highest, showing the highest 28 IU per GDS of filter paper activity in within 48 hours. I'm sorry, 48 hours. And then whereas 12 IU per ml activity was noticed at highest 96 hour in case of control where no nickel ferrite is added. Then similar results we obtained in enhanced enzyme production using observed highest endoglucanase activity on in 48 hours, that is around 152 IU per GDS, and then in case of beta glucosidase we got 48 hour around 212 IU per GDS activity. So it is this observation clearly indicate the significant impact of nickel ferrite nanoparticle on enzyme production. Then we did analyze the role of temperature as one of the crucial parameters for cellulose production here in this slide, figure A, is we notice that 40-degree all in all is crucial for high efficient enzyme, let's say, activity for in terms of temperature. And we also noticed that enzyme production was enhanced almost 50% using nickel ferrite nanoparticles. While in case of crude cellulase, we tested with in presence of nickel ferrite nanoparticles in figure D. So, I'm sorry, it was a network issues with that. I'm really sorry for that. So in terms of the crude cellulase activity, we noticed that nickel ferrite mediated treated has optimal activity on at 65 degrees centigrade here. And again, we noticed that the optimum activity was for incubation temperatures between 50 to 65 has also been reported in most of our previous work. Then we also did the thermal stability of the crude cellulose at a temperature in presence of 1.5% nickel ferrite nanoparticles. And we noticed that here is figure 1, where is more thermal stability between, we observed that it has whole half-life. This nickel ferrite treated cellulose holds its half-life at almost in 80 degree, and on contrary to the control, which is actually 65 degree, which is here. And in case of figure B, which is more about it, we observed that a nanoparticle mediated treated enzyme showing thermal activity of 100% at 65 degrees centigrade and up to 3 hours. In figure C, you can see the effect of nanoparticle on pH stability of crude cellulase enzyme, which is evaluated at different pH. So we noticed that pH between range 6 to 7 was giving optimum enzymatic activity with the hull, and then this is very much evident that enhancement in pH stability, the role of the nanoparticle, especially the nickel ferrite, plays a very important role, and if that include the efficiency of crude cellulase to achieve higher biohydrogen production. So then we also did analyze the different pH as a factors for production of this cellulose, and then application to these for biohydrogen production. So here in figure A, thermal stability of nanoparticle, nickel ferrite nanoparticle was treated with crude enzymes and in treated cruise control were examined between different ratios with the glucose and then ratios of glucose and xylose and arabinose, and we noticed and produced crude cellulose from fungal strains subsequently with nickel ferrite mediated antibodies were evaluated for sugar production using this enzymatic hydrolysis of alkali treated rice straw, which is we got almost 28 gram of in 12 up to 28 gram of per liter of glucose, about 20.6 gram per liter of xylose, and 1.8 gram per liter of arabinose, suggesting that 12-hour treatment with nanoparticle has significant impact of enzyme on enzyme enhancement. In figure B, the produced fermentative sugar hydrolysis had been directly used for substrate to produce biohydrogen, and in batch fermenter to dark fermentation using bacteria, one of bacteria Bacillus subtilis, under the most favorable condition at 37 degree temperature and pH 7. You see it has got 1820 milliliter per liter of cumulative biohydrogen production in 192 hours. The maximum, also we noticed that maximum hydrogen production rate was 19.92 milliliter per liter per hour was recorded in 24 hours. So overall, we emphasized numerous aspects of implementation of nanocatalysts and nanoparticles as possible as the possible approach to elevate the integrated technology for enhanced biohydrogen production in a sustainable way for its practical application in near future may change this scenario or getting higher fold increase in biohydrogen production for energy, biohydrogen as a source of energy. Thank you very much.
So we would like to thank Professor Vijay for his talk. So we come to an end of session 1C. So we'll start with session 2 at 10:30 sharp. So we'll take a short break as of now, and we'll be starting with the session 2 at 10:30 a.m. So please be online, whosoever is there. Thank you so much.
सर वो तो इसमें आई नहीं. सर 12 वाले का फिजिकल नहीं है हमारे पास फाइल. ये 12 13 10:30 right? Two minutes left. Yeah. Yes sir. तुम अमाउंट स्लाइड ऑन करो. मैं कर दिया मैंने कर दिया. Please progress.
You're recording?
Yeah.
Okay.
Perfect. 30 minutes, right? Yes. Give me the hint.
At about 25. Okay. Yeah, yeah.
Welcome back to all the delegates, those who are present with us and those who are present online all around the globe. So we'll start with the session 2. And our first speaker in session 2, who will be delivering a plenary talk, his name is Professor DJ Lee, and he's from Taiwan. And his plenary lecture is on degradation of high-strength acrylic acid-based water with anaerobic granulation technology. So I would request Professor Lee to deliver his talk. Over to you, Professor. Thank you.
Thank you, Mr. Chairman. This talk will be regarding the degradation of high-strength and recalcitrant wastewater with the particular technology called anaerobic granulation. So, well, this is a very old technology, and then doing the very old traditional wastewater treatment, but it had new concern about how and why. Okay, so this talk will be something like the very, very old materials, but something we need to put attention on. And then, so this will be presented by me as well as Dr. Xiu Guang Yao. It's from Puritech Collaboration, my industrial collaborator. So, well, wastewater treatment had been applied for over a century, and then about something like over 70% of the urban wastewater treatment are being implied by biological treatment process. So the annual revenue is quite big, $60 billion US, so it's good, very attractive. So it's good market. And then, so the cost is very cost effective using the biological treatment process. Normally we claim for the BOD divided by COD greater than 0.5. We call it biodegradable. So we do the wastewater treatment using a biological treatment process if they are biodegradable. This is reasonable, right? This sounds reasonable. So wastewater treatment, normally we say that using the aerobic treatment for urban wastewater. But in case we are talking about recalcitrant compounds in the high-strength wastewater from industries, normally we're talking about anaerobic treatment process with no clear idea why, right? But just practically useful, and practically aerobic fail. Anaerobic works. Okay, this is the practical experience tells us. And this kind of stuff had already been there for century. But an interesting part is that in case you check the standard textbook, they'll say the BOD divided by COD ratio, or B over C, is the index for biodegradability of the wastewater or the recalcitrance of the wastewater. So in case you check the standard textbook, they will say greater than 0.3, okay. Less than 0.1, don't think about that. You should do physical, chemical precipitation or whatsoever, or advanced oxidation, but no biological treatment. But this is not true in case we are looking at the current and then the past experience, because there's so many practical experience that we can actually handle the very recalcitrant wastewater by anaerobic technologies. So, okay, then we very briefly talking about the, okay, so very briefly, we have the aerobic, anaerobic, and then suspended and fixed film, okay? So in case you check the literature, you will find that, so in case we are talking about the low COD, BOD application like urban wastewater, that corner will be suspended aerobic applications. In case we are talking about the high-strength, recalcitrant wastewater, there will be fixed film, and anaerobic treatment this side, okay? So, well, interesting, why and how? Okay, then very briefly, aerobic and then anaerobic. Well, we now have the niche for anaerobic. For example, the energy production, anaerobic can produce energy by methane, or fermentation can by VFA or hydrogen. But the COD, for the aerobic one, we just put all the COD to CO2. So it's good for the wastewater, but no good for energy recovery and all the global warming. And also particularly because the anaerobic process can have a high loading rate. So the land used will be much smaller than the aerobic counterpart. Okay, these are niche for the anaerobic process to the aerobic one. And then, one issue is that in case you check the literature and then practice, you will find that the anaerobe, they tend to agglomerate into some kind of the biofilm or aggregates. So they can be used the USB and other kind of, we call the high rate reactor, because you can actually decouple the HRT and SRT in the process. So this is good way. You can, you have to do the recycle to control, to decouple it in the wastewater activity such process. But an anaerobic one, no need for that. You have the granules. So the granule or granulation looks like playing some essential role for treating the high-strength recalcitrant wastewater. Okay, so when you're doing the granulation, okay, anaerobic, well, actually, our group did the aerobic granulation a lot. And when we're talking about anaerobic granulation, some mechanism work, some mechanism cannot apply. But basically, the theory is very similar. You have to have some individual cells to form some micro and nuclear, and then have to embed it in some kind of secreted EPS, or then you have to glue more, and then blah, 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 something like that. And then one difference, major difference, is that for aerobic granules, you can have layer structure. For example, outside you have the aerobe, and then inside for anaerobe layers, micro enriched layers. But for anaerobe granules, no such kind of the layers, because everybody, everywhere, there are no oxygen. Okay, no oxygen. So the difference will be depending on neutron instead of oxygen. For aerobic granule, depending on oxygen level instead of the neutron. Okay, so these are difference. But basically, the mechanism will be similar, but the driving tendency for the driving force will be different. So the rule is that we need to have something like the 1 to 3 millimeter mature granules, and then your reactor will operate well, and then provide very sufficient performance, or regarded it is recalcitrant or not, okay, high strength or not. Oh, these are the kind of the applications. So you see, they are very, very old names that you already learned from the first year in the civil environmental courses, wastewater treatment courses, and for the UASB, EGSB, and etc. They are being applied in IC. Okay, so these are the kind of the granulation, and then so you see that these are very old, mature technologies. Okay. Okay, then we can see the model. Actually, no such kind of model. And we can see the condition. We'll skip this first. You can have time coming back. You see how they can be cultivated. Very different from the aerobic granules. In fact, in case you have experienced that, in case you want to cultivate the granule in the anaerobic system, it's not so easy. You take months, sometimes years, okay? But once you form, it will be very stable compared to aerobic granules. So very difficult to form, but very stable upon the kind of shock loading and then kind of operations. There are some tricks. There are some tricks to accelerate it, okay, including the alternating feeding and then the swinging of the temperature, etc. The basis is that to torture your microbes, and then they will try to form granules. Okay, the key is something like this. That's looking like don't give the good time to live, and then they have to collaborate together to fight with the environment. So this is a similar way. But the tricky part is that the swinging the COD up and down look like the most efficient way to accelerate the granulation. It can cut down from maybe 3 to 4 months to less than 1 month, okay, in case in doing that. But there are case by case. We have actually now 3 systems this strategy work. But this is going to skip here, and then inoculant and something, and then kind of something like that. Okay, then for in case you form the granules, and this kind of this literature, recent literature, I think means recent means that recent 3 years. You're going to the renowned journals like the BT, like water research, like this. These are the kind of the fields you find the wastewater, they're being treated by the anaerobic granule system, anaerobic granule system. And they are high strength. High strength indicating that normally we call COD higher than 10,000 milligram per liter, okay? In the normal urban wastewater, we are talking about something like the 300, 400 milligram per liter, but now it's a 10K above, okay? This is called high strength. But high strength, not necessarily that they are recalcitrant, means that they may be biodegradable, particularly for the like a brewery, like a kind of the bakery wastewater. They are quite, we did some kind of the bakery wastewater treatment, and then we collect the sludge, and then we dry the sludge, and the smell is very good. A lot of yeast, a lot of things, just okay, like a baking the bread, okay? So not necessarily the sludge is bad, no, not necessarily, depending on the wastewater. But they are high strength, quite high strength. But they are not recalcitrant, means that they are biodegradable. It's okay. I mean that their BOD is quite high in the fraction of the COD, maybe 70, 80%, okay? So they are not. But this kind of granulation, in case you look at literature, they are good for high strength wastewater, okay? But in case we cut into, say, some will be recalcitrant, some will be biodegradable, then it will be different story. Okay, so I want to clarify the idea. Say, okay, this is impractical there, so for centuries, so why bother? We are not talking about not only high strength, but also recalcitrant. Okay, then coming out one issue. In case the compound in your wastewater is high strength as well as recalcitrant, why it can be degraded? You tell me it's not degradable, right? The textbook said then don't try, because that in case of high strength and recalcitrant, don't try it, okay? Using the precipitation to sludge, take away, or oxidation, or using the H2O2 and UV, whatever, right? Don't try biologically. But actually they work. And why? And why? So then they come out with the, okay, these are the kind of the recalcitrant wastewater, like from pharmaceutical, like the textile and dyeing, and then like the specialty chemicals, the core chemicals, petrochemicals, etc. Now recently, these have been widely used in particularly my collaborator, Dr. Xiu Guangyou, I think that you know him very well, a company particularly in China. So they have many kind of application for this in the high strength and recalcitrant wastewater. And then why? Why this can work? Okay, we work on this for over 15 years since I visit Singapore, and then starting to work on this project for them, and then till now. Okay, till now. So it's a long story, because you know, in case that you don't have much time, don't do that. This is a slow process. Anaerobic process is slow. Okay, sometimes you just cultivate for a few months, you can get nothing. Okay. But this is once it's very good. Aerobic one rapidly you can get something, but anaerobic no. So this, and then also you see some kind of the chemicals. They are the typical compound in this, we say, recalcitrant wastewater. And then today I will show you one example is the acrylic acid production wastewater treatment we are showing later. So these are the recent publications for the recalcitrant wastewater, and you see the wastewater and the COD and high, and then something like the 100 plus 100K, okay, something like the milligram per liter, blah blah blah, many kind of, and all of them the same is that the same index is something like the BOD divided by COD ratio is low. Okay, so they are high strength. And we are talking about recalcitrant. So the BOD-COD is low, indicating that no, they are not suitable for wastewater treatment. But when you check their results, sometimes a 99% removal. How come? How come the non-degradable things can be degraded by your micro? You are Superman or something. some interesting curiosity come out this one. So there are some kind of conceptual misunderstanding inside that. I can tell you the answer we think about is that, in fact, BOD is not an adequate indicator for anaerobic treatment. What is BOD? BOD is measure the dissolved oxygen level change under the kind of the biological degradation. So it is for aerobic organisms. So they use the oxygen. So for anaerobe, they don't use oxygen. So the DO is not the proper indicator. So up to now, actually, no proper indicator for the anaerobe recalcitrant for the wastewater up to now. Okay. So this just to show you an example. Then this come out of curiosity, and then these are the kind of the compound commonly you find in the recalcitrant wastewater. So they are commonly have the benzene ring. They have some kind of the prohibit the meta subscription, etc. Many kind of you can see they're common, and then they are all have good removal, but they are very, very difficult to degrade biologically. Okay, so the question is that, by the BOD. Okay, BOD very, very low. In case you put it into the BOD test. So these are the we summarize here. Okay, so this come out with the a claim that or a kind of discussion about compound recalcitrance. Recently, there's a paper published in Science, I think. Yes, they found a bacteria they can secrete a kind of specific enzyme can degrade PET. Okay, so PET should be recalcitrant, right? Because we say that the plastic be there for thousands of years, will not also be. Oh, now we found somebody. It's not a engineered bacteria. It's a wild strain, just very few. Okay, they can degrade PET. So now you tell me PET is degradable or not? It in fact that it's not readily degradable, but common consortium you made in the environment. But some can do that. And the other, you will find that they will tell you other kind of the PTFE or whatever can be degraded, but at a very, very low rate. So these still be considered recalcitrant because that we cannot degrade it in a reasonable time frame. But they are not non-degradable. Okay. So actually, for survival, microorganisms they strive to find any way they can survive. So maybe they can, in case otherwise they just perished. So they try to do that. So in case you are talking about this one, it's within the kind of the reasonable time frame, say, in case you HRT, it's the 12 hours to 1 day. Okay, or in case otherwise that maybe it's not economically feasible. Okay, so you can do that, but there's a very much operationally defined value. It depends on how you want to define it. Even BOD is the operational defined value, 5 days or something like that, right? 7 days or something like that. So in case about this, it's not the, of course, the DO is not the kind of the proper indicator. So you see the box here. So to the right is the x-axis is BOD to COD. So we talk about in our textbook above 0.3 will be biodegradable. It's aerobic biodegradable, but less than 0.1 we say is recalcitrant. But actually, in some of them, in anaerobic condition, they are still degradable, but not probable by this indicator. Okay, so this kind of indicator is not available yet, but so not the BOD divided by COD ratio low will be non-degradable, but definitely they are aerobically non-degradable. Okay, so different. So okay, this clarifies something. Okay, for the one, for under the anaerobic condition, anaerobic conditions, and then whether or not they can do the job. Well, our experience is that it really depends case by case. But in case you are having good strategy, normally you will do that. Means that you can cultivate some consortium can degrade your recalcitrant compound anaerobically. And then how to sustain the high strength? You need granulation. You need a functional strength to degrade the recalcitrant compound so they can be degradable, right? Otherwise, that you cannot degrade it. But you have to suffer or have to resist the high strength shock loading or whatever. You need the granulation to protect your microorganisms. So these two issues, anaerobic, granulation, actually both are important. Anaerobic means that only anaerobically you can degrade it. You have to find the consortium. You have to incubate that, and then you want to granulate them to form an aggregate to resist high strength challenge. Okay, my time's up. Not yet. Okay. 4 minutes. Okay. Then I show you one case study. Okay, this is from a real plane already operate for 8 years, and then it is using the influence COD. It's an acrylic acid. It's a major raw material for this process, and the wastewater coming out is something like the 20,000 milligram per liter COD, and then the BOD very low. Actually, this BOD COD ratio is less than 0.05. So it should be no consideration of the biological process. But this process, we're using the combined process for anaerobic and then for aerobic to polishing it. Together, it can reach 95 to 97 COD removal. So this is the wastewater parameters. And then, because the local host, I mean the company, this is full scale one, okay? They also want us to treat their waste oil together to solve all the problem. So in the process, we are doing that beside the wastewater acrylic acid, in between we also add the oil to see whether or not they can solve two together and then to kill everything together. It works, it still works. So you see the BOD, you see here the BOD is about something like the 0.6 or whatever, very quite low. And then finally, and then also the pH or whatever, okay. And this is the full scale one. I cannot see actually here. When you're coming in and then you put into your, to adjust the pH and then to, why we have the sanitary sewage, because we want to dilute it. The initial one coming in is about 220K milligram per liter COD. And we dilute to 20K, okay, milligram per liter. Otherwise, it's still too strong for that. And then coming into GSB. GSB is the anaerobic reactor. So they will produce methane. Methane now is flare. It's flare. And then in this stage, GSB stage, it removed about 97% COD. HRT is about something like, I remember it's less than 1 day, okay? And then you see this recalcitrant wastewater, okay? And then the final CBR and ASB actually is an aerobic reactor. They remove another 2%, so reach 99% removal. So this is the, you see the cartoon here showing the anaerobic one and then to the aerobic one, okay? Both are fixed film reactors, but so the quite tiny one. The treatment, remember, is per day is 500 cubic meter per day, okay? But very high strength wastewater. So this is the real plan there, and then the granule, the foam is dark, okay? Anaerobic one is dark. So the total investment is about $4.5 million US, and recover period is less than about two and a half years. Recover all the. Now it's about 8 years, so they actually earn good money for this process. And this is the start period, and then also the long-term test. So the quite stable actually, quite stable. And then you have the influent wastewater coming up and down, but always they are high strength and recalcitrant. And basically they are acrylic acid molecule. It's BOD very low. But well, you can see the most of the acrylic acid gone. Okay, so this gives you an idea that in case you have the consortium can degrade the acrylic acid and also form the granule, then even this Sharky loading, and then so just mention about how long. This data been tracked by almost 1 year, but then operate another 6 years and a half. Up to now, I think it's about 8 years plus. Okay, no problem, because the biomass grow very slowly, so there's no sludge discharge ever. And okay, great. So well, okay, this is the thank you, and then because you see the keywords: high strength, recalcitrant, anaerobic granulations. Thank you for your kind attention.
Thank you so much, Professor Lee, for your wonderful presentation. Now, if there is any question from the audience, we can take it. Okay.
Hello, Professor. I have a question. In the presentation, you mentioned that the anaerobic granulation technology can be used in fermentation, bakery, dairy, so many things. But generally, they contain very high BOD. So, but according to your presentation, the BOD should be less, or BOD-COD ratio should be less?
No.
Then only
No. Actually, it's this one. Anaerobic indicating that you go anaerobic pathway without the oxygen. So in case you have high BOD, then your granules will full of the fermentive bacteria and others, so you can form VFA, H2, and the other kind of, and then to methane.
Okay.
Yeah. In case you are low BOD, indicating that you need the functional strength to degrade the recalcitrant compound, then go to the following the same, the cycles. So the anaerobic just very good for handling the high strength wastewater. Why? Okay, the reason actually is that for aerobic one, the limiting, just like the Professor, just like Samuel mentioned about nano bubble, he can enhance the mass transfer rate for oxygen. So oxygen is actually limiting the aerobic granules or aerobic consortium degradation efficiency. So they rapidly consume the oxygen. So they cannot provide higher degradation rate. So they cannot provide the high treatment capacity. But for anaerobic one, there's no limitation for this. But the high concentration outside, they can diffuse faster into the granules. So higher the better, except the substrate, we'll call it substrate inhibition occur.
Okay.
Yeah. So there are still, but the one issue still, in case you can ask question maybe, but I mean the boundary is not at the high strength. The boundary is, we're talking about, is the part that everybody know anaerobic granule can treat the high strength very good. But why recalcitrant one can be treated as well? Yeah, in case it's low strength, it's also okay. But in just the anaerobic one, they prefer high strength. They can have the advantage.
Okay.
Yeah.
Thank you.
Any more questions?
Oh, okay.
Yeah.
Very interesting talk, teacher, indeed. One of your last slides, you mentioned that the reactor is operative since almost 8 years now.
Yes.
It's remarkable. But does it mean that there is practically no cell growth, even that is under anaerobic condition? Then how there is a continuous performance, or there is a very negligible growth and equally there is a cell washout which has not been perhaps monitored? How you relate this?
Okay. For 8 years, we do not really monitor the from year 2 to year 8 because they already put to operation, and then the field the operator, they will monitor the COD, and then because they have fit the discharge standard. And for us, this is the first the data we run out, so we people are there and take a sample every day, blah blah blah, so we can see they are stably. But from the field, we learned that most of the microorganisms, they degrade the carbon source for their metabolic need, not for the growth. this is a very this is one that we also observed in the aerobic granules, that when the microbes they live in the compact space, they tend to just stay living without reproduction. So these granules, when you form, firstly they grow very fast in the biomass, and then they just level off and grow very, very slowly. I think the yield will be less than 0.02 or something, very, very low comparatively. So to the big reactor, they can suffer this kind of the increase. I think a few years there no need for discharge of this. Of course, that maybe some already dead and then I don't know, because we did not follow this in the. But it's interesting to see that. But one issue for present today is that we actually had another two successful cases, and then the one actually this one figure published in BT, okay, BT. But why I'm presenting BT? Because I think this is an interesting question. Yeah, when I was taken many years ago, I said, hey, it should not be biologically treated. Then why you do that, right? But successfully, it's very good. Hey, and then you check the papers. They just say, okay, you check a standard paper, okay? They say, I will establish a reactor and then do the test, and then I found it very good. COD remove 95%, blah, blah, that's it, right? But we check what you are input in there. It may be degradable, maybe recalcitrant, but nobody cares. And then we're talking about the textbook, it says BOD ratio, right? But it should not be, okay? Then coming out, because why I'm talking about this, another issue is that the my collaborator, Dr. Shou, just 30 seconds, okay? His company is very successful in China, very, very successful, big money. Why? Because that most of the company, they assume, this kind of wastewater from coal chemistry, from the, no possibility for biological, don't try, okay? So they use the chemical precipitation, other kind of things to do the sludge and then take away, something like that. They don't even try it. But this company, they try, and it's successful. We actually did this in Singapore already, and then it's still always, why we can do that? I don't know why. Successful, and then why? And then finally, okay, why? Because that BOD is not a good indicator at all. It's only good for aerobic treatment. So in case BOD is low, so don't try anaerobic one. Oh, no. But I don't know why. This is a quite common misconception, okay, to me, sorry. So then we try to highlight this one and then say, in case that you can have a good consortium, and then so two parts, anaerobic, good consortium for treat the, and then for granulation to sustain high strength. Yeah, and then successful for many cases. There are almost 80 full-scale plants over China now, still growing. Okay.
Thank you so much, Professor, for your talk. So we'll be moving ahead with the next presentation. So our next invited talk is from Professor Deepak Pant from Belgium, and he'll be presenting online live. He's with us right now, and he'll be delivering a talk on bioelectrochemical systems for wastewater treatment and resource recovery from lab to field applications. So I would request Professor Pant to just share his screen so that we can hear his presentation. Over to you, Professor Pant. Pant, can you hear us? Yeah, you have to unmute yourself. Yeah, Professor Pant, can you? Hello, Professor Pant, can you hear us? Okay, here. Audio. Okay, Professor Pant, you can start your talk. Thank you. You can share your screen. We can't see your screen, Professor. Yeah, we can wait for 1 minute. Is there? Okay, Professor Pant, now we are, yeah, you can share a screen now. Okay. Speaker. What are you doing? Okay, just let him speak. Okay. Dr. Pant, we have allowed you to share your screen. So you can share your screen. We cannot see that. There must be a share option at your end. Yeah, yeah. Thank you. Yeah, yeah. We can hear you as well as we can see your screen, but it is requested to just cut short your presentation so that everything is on time. Thank you so much. Thank you.
My topic is biomechanical systems for resource recovery, field applications, and quickly I will move to the next slide. So I work at the Flemish Institute for Technological Research, VITO, which is located in Belgium. It's a RTO, it's not a university, so research and technological organization, and we are working on 5 main areas of materials, energy, chemistry, remote sensing, and human health. And I belong to the unit of sustainable chemistry. The main idea is to use auxiliary resources and renewable feedstocks and to replace fossil feedstock as much as possible. To make, and the chemical industry is quite big in Antwerp, so it's one of the largest chemical region. And the main idea is to reuse, replace, and recycle the waste materials and to come up with the new feedstocks. So in terms of feedstocks, We have identified 3 main lines. One of them is biomass, and among the biomass, what the main feedstock we are working on is lignin. We have established a center for excellence called BioHorizon, and the second feedstock is carbon dioxide, which I will speak a little bit more about in the presentation. And third one is about microplastics, especially microplastics identification and finding their replacement in terms of process transformation. We work on process intensification as well as using test methods. Now, coming to the main topic, which is bioelectrochemical systems. As you can see, this is a typical bioelectrochemical system with a two-chamber setup with an anode and a cathode. At the anode, you have the oxidation taking place. At the cathode, reduction taking place. Now, depending on the type of the reactions, on the combination of these reactions, you can have a different types of bioelectrochemical systems. So one of the 4 fundamental types is a microbial fuel cell, where you oxidize the organics present in the wastewater and convert it into carbon dioxide. And there is a special class of electroactive bacteria known as Geobacter or Schwannella, and there are several others as well which have this ability to transform this organics into carbon dioxide, but at the same time transfer their electrons extracellularly on a solid piece of electrode. In this case, when the electrons pass through an external circuit and they reach the cathode and they combine with oxygen, oxygen acts as an electron acceptor, then this is the concept of microbial fuel cell. On the other hand, you can have another class of bacteria which accept electrons from the solid electrode, such as Sporomusa and a lot of homocytogens. In that case, the chaotic reaction most of the time is oxygen evolution, and you convert CO2 into products, right? So then it's known as microbial electrosynthesis, and this is one of the most recent topics in biochemical systems. Now, as I said, depending on the type of anodic oxidation reaction or on the cathodic reaction, you can have a lot of application for these systems. And these applications find in wastewater treatment, which is the microbial fuel cell I mentioned. Then you have resource recovery from wastewaters. So this can be a microbial desalination cell where you convert seawater into pure water by taking out the ions. You can have electricity-driven bioproduction, which is just another name for microbial electrosynthesis. You can find this application in bioremediation as well as biosensing. Now I'll start with the bioelectrochemical systems for wastewater treatment. So this is a typical setup of a microbial fuel cell that I showed you already earlier, where the bacteria consume the substrates such as glucose or acetic acid. And as a result of their metabolism, they produce electrons and protons. The electrons pass through the external circuit, like I mentioned. Protons goes through the membrane, and at the cathode side, you have the oxygen acting as electron acceptor, producing pure water. So this is in general the basic concept of MFC. In terms of substrates, the most favorite ones are acetate, starch, and glucose, but hundreds of different types of wastewaters have also been explored, such as paper mill, dairy, bakery, brewery, you name it, and it has been tested by someone in the microbial fuel cell. When we started on this topic, one of the main so the whole system was the high cost of cathodes, because everybody was using platinum-based electrodes for oxygen evolution, and also the membrane, which was most of the time naphthalene, which is quite expensive, and especially when you are using it for such low-end applications such as MFC. So then we started working on developing non-platinum based electrodes, and we have developed a portfolio of almost 8 to 10 patents right now, where we have found an alternative gas diffusion electrode just based on activated carbon without any platinum group metal, and we can upscale them to meter square, as I will show. This is how a typical gas diffusion electrode looks like, where you have the 3 layers, a hydrophobic layer, which allows only the gas to go from one side to the other side. Then you have the catalyst layer, in this case activated carbon, where the reaction takes place. So this is where the 3-phase contact happens, and then a current collector. In physically form, this is how the electrodes look like. The white layer is the gas diffusion layer, then you have the current collector, and sandwiched between the two is the carbon layer. Of late, we have also worked with the electrocatalytic CO2 reduction, and for that we have prepared metal-based electrodes such as based on copper and tin. Okay, so we have quite a large production facility for these electrodes. We can go from PL1 to PL7. So this is at the bottom left is the production facility. And this is the size of electrodes on top. You can see from 10 centimeters square, we can go up to meters square. And these electrodes have been tested by almost more than 45 products all over the world. Then we also do a lot of stacking. So starting from very small cell for testing the electrocatalyst and bioelectrocatalyst, we make a larger cell and then we make stacks up to 16 meters square. Now, this is how the electrodes was started story at Vito. We now call it, we have given it a commercial name. So the electrodes are actually available commercially. This is known as Vito core. Core stands for cold rolling, which is the method with which we make the electrodes. And here you see the comparison of our electrodes, which was done by Professor Bruce Logan at Penn State, without Vito electrodes, without any PGM, and their own electrodes with platinum. And there is not a big difference in the power density that you can obtain, right? Then we also, like I mentioned, we have tested them for a very long term performance, almost 18 months. So of course, there is a little bit drop in performance because of salt deposition on the current collector side. But once you clean the electrodes with DI water, just rinsing it, the salt is removed and the performance is restored. And of course, we can, depending on the requirement, we can add some other salt and pepper to the electrodes, such as iron or carbon black on the activated carbon. This is just to give an idea of the scale in which we can work with. So this is the standard cell that almost 90% of the people work with. This is a cube reactor, as they call it. The electrode surface area is 10 centimeters square. Then you can make a little bit larger, 100 centimeters square. And this is something, the largest MFC single panel electrode. This is almost a meter square electrode. This was tested for two main conditions, which was first, there should be no water leakage to the cathode side, so no water should come on the gas diffusion side at a water pressure of 1 meter, which was achieved. And the second one was when you go from this small size to this large size, the drop in current should not be more than 10%. So both these conditions were fulfilled eventually by us, and then we'll go to the next one. Yeah, and this is how it was tested. So here you can see this is the largest scale 255 liter reactor, which was tested with a real municipal wastewater. In the center is the brush anodes, and it was sandwiched between two cathodes of this size. And this was also run for 3 months time. So that was quite a good performance. This was done in Germany at Ruhr University of Bochum. Then in terms of MFCs for sanitation application, so this is a bioelectric toilet developed by our partners at IIT, Professor Evan von Reker. And this has been in operation since 2017, so 5 years now, where the human physics and urine passes through the bioelectrochemical system or microbial fuel cell, you can say. And this is the real picture. I visited it before the COVID in 2019, and the clean water is then used for flushing here on the top. So this is a quite nice demonstration of a pilot scale field application of a microbial fuel cell. And all these reactions are happening there, right from carbon to ammonium to sulfur removal to disinfection, and of course the oxygen reduction, which is the standard cathodic reaction. Because I have to go fast, I'm looking at the time as well. I will also talk very briefly about the CO2 conversion, which is the microbial electrosynthesis part. Now, we started on this topic in 2015, I would say. The main reason was, again, not only to use CO2 as an alternative feedstock, so to speak, but also combine it with the renewable electricity. Now, this is the typical microbial electrosynthesis system where CO2 is the feedstock, and you can convert it to alcohols, organic acids, bioplastics. Now, you can see the interest in this topic has been exponentially increasing over the years. So, this topic came into being in 2010, and now this is the number of publications. If you look on Google Scholar, it's increasing with each passing year, with a lot of research also being published in bioresource technology. In terms of the things that influence the performance of MES, again, it depends on the inoculum source, inoculum pretreatment, which type of reactor you are using, what are the operating conditions, which type of operation regime is fed batch, continuous, and of course, electrode materials. So we focus being our expertise on electrode materials. We started thinking of developing electrodes for MES as well, and we defined another type of gas diffusion electrodes for microbial electrosynthesis as well, where instead of passing oxygen, we were passing now CO2. And we tested these with all types of catalysts, including enzymatic, bacterial, and electrocatalyst. And we saw that there was the supply of CO2 is much better when you use gas diffusion electrodes instead of supplying CO2 just by bubbling through the electrolyte. So when we combined this with a gas diffusion electrode, we got high acetate production, around 10 grams per liter of acetate. Then we started a project with an Indian company called Indian Oil R&D Center in Faridabad, who tested our flat planar electrodes with their special type of a mixed consortium. And this is the result that we obtained. So initially we produced a lot of C1 compound, which means formic acid, but over time C2 like acetate ethanol also started appearing. And after 90 days, you can see more than 70-80% of the product spectrum was only alcohols. Now this company is mainly interested in alcohols because then they can use it for blending with the gasoline, which is also mandated by the government. They have to go up to 20% in by 2030. Now there was a paper that came this year, a review paper, combining or mentioning the main products that have been produced by CO2 conversion in MES, starting from acetate of isopropanol, methanol, and our results from butanol, methanol was the highest that we obtained in 2018. With this company, we filed a patent in 2019 where we combined a new design of a gas diffusion electrode, which is a tubular concentric ring. And this patent, a European patent, was just granted 2 months ago. And based on the technology that we developed, now they are running a pilot of 500 liter in their facility in Faridabad. So this is our several reactors which are combined in stack, as you can see. And the idea is we are still waiting for the final demonstration result. The idea is we should be able to convert a lot of CO2 in a defined amount of time to a mixture of alcohols. And for them, the standard, they consider the system as stable if we can run it for more than 3 months. So that's really in the industrial setting. And I'm looking forward to those results soon. There's a European project that we finished recently. Then we went one step further and we tried to combine not one but several of these type of electrodes in one reactor. So this is a bioreactor. The special thing here is we could pressurize it to 10 bars. By pressurizing it, we can improve solubility of CO2 and hydrogen in the electrolyte and make it available for the bacteria. So we developed this 1 liter reactor that is now in my lab, and we tested it for ethanol production, the genetically modified Clostridium, and you got excellent results, which are just pollution control system communication. Finally, the last 2 slides I will show is that we also help some artists who wants to show the use of bioelectrochemical systems or microbial fuel cells. So this is a design or drawing by Teresa van Dongen, which is a designer based in Amsterdam, where she make these lamps called Spark of Life, which is again based on the concept of microbial fuel cells. And what you see here are the tubular electrodes developed by Vito. Another design, this is called Electric Life, and she's selling them commercially. And there are bacteria inside these reactors which use glucose as a carbon source, and based on the power generated by these systems, these lights or LED lights glow in the dark. So this is a nice demonstration of microbial fuel cells. And the final slide, I promise, is about the combination. So instead of just using bacteria and asking them to do everything, we are now combining the approach of combining classical electrolyzers with bioelectrolyzers, which means we first convert CO2 using electrolysis into a steam form such as formic acid or syngas, and then in the second step, then we use the biocatalytic fermentation reactor for converting CO2 or this formic acid or syngas into higher carbon molecules like launching commodity chemicals. So this was the concept. And based on that, we are now involved in a project that started beginning of this year called Vivaldi, where we are involved in conversion of CO2 into methanol and formic acid. And then in the second step, our partners will use this to convert it into hydroxypropionic acid, lactic acid, succinic acid, and itaconic acid. So this is the combination. So this hybrid system is really the next step, next frontier for CO2 conversion, I would say, and shows much promise. So if I summarize the work we have done, it's so about the Vito gas diffusion electrodes. Like I mentioned, we have a family of 8 to 10 patents right now. Initially, we started in microbial fuel cells, but of late, we are now working more on CO2 reduction and electrosynthesis. We can make them up to upscale sizes of meter square. And apart from us, a lot of other universities, industries have used these electrodes. Some of the examples are mentioned on my slide here. So this is our team, which is involved in all these projects that I showed you. Partners I could not mention, but funding agencies are mentioned here. I would like to thank the organizers for the invitation to present our work today, and I apologize for the inconvenience caused at the beginning because of bad connection. If you want any questions, thank you.
Thank you, Dr. Pant, for the wonderful presentation. Since we are running out of time, we are skipping the question and answer session. Those who have any queries, you can contact Dr. Pant via email. So we will move to the next
Absolutely.
Thank
you.
Invited lecture, IL-15 by Patrick Drogi from Canada. He will be presenting online on his topic, EPS production and its application for landfill leachate treatment. Over to you, Professor. You can share your screen now and your PPT.
See something right now? Can you see something?
We can hear you and we can see your screen.
Okay, thank you very much. Okay, it's a pleasure for me to be here today to share with you our research activities dealing with EPS production and its application for landfill leakage treatment. And this work is a small part of a PhD work of Anusha. So, first of all, I would like to fix the context to explain you why you would like to use EPS to treat landfill leakage. As you know, landfill is a key method for solid waste management. And you have to notice that 25% of municipal solid waste in Quebec is organic in nature. And around 80% of municipal waste in Quebec is landfill. And 30% of Canadian population use groundwater for domestic use. As I present to you this data, is very important to manage solid waste because during the management of solid waste, you can generate leakage that can be that can contaminate surface water or groundwater. So it's we need to be carefully manage this landfill to avoid water contamination. Okay, as I told you, in landfill leakage, we can find higher concentration of nitrogen, heavy metal, and organic matter. And this type of effluent can be very toxic. And it can be a very big source of the contamination of groundwater and surface water. So, what's happened? I cannot change my slide. Oh, what's happened? Okay. So the specific objective of our work is to investigate EPS production using different types of substrates, such as crude glycerol, waste cooking oil, or activity sludge, and also to optimize the different parameters during fermentation. The second objective is to see the performance of the treatability of landfill liquid while using EPS. Okay, the most important point is to understand very well what is EPS, extracellular polymerase substances that we will like to use. You have to notice that we have two types of EPS. You have soluble EPS and you have broth EPS. Okay, the soluble EPS is tightly is weakly bound to the cell walls compared to the capsular EPS. The capsular EPS is tightly bound to the cell walls. And the third EPS is what you call broth EPS. It means that it's a mixture between capsular EPS and soluble EPS. So it's very important to see the different type of EPS. SLAM EPS, weakly bound to the cell walls. We have also capsular EPS, tightly bound to the cell walls, and you have broth EPS, is a mixture of capsular and soluble EPS. Okay, now let's talk about the methodology quickly. Let me put in the. Okay, to produce EPS, you use different type of substrates. Sludge, activated sludge, waste cooking oil, or crude glycerol. And these substrates can be introduced into a chicken flax, okay, containing a strain of bacteria, and we submitted this mixture to the fermentation. After the fermentation, we have centrifugation step, and after centrifugation, you can have a next step consisting to dry and make the calculation to evaluate the concentration of EPS. After that, it's possible to use the EPS to treat wastewater or landfill leakage. Okay, so here I present you the different steps of our work. The first step consisting in producing of EPS, and the second step is to collect the landfill liquid, make the characterization. After that, you can use the EPS to treat this type of wastewater. Okay, you can see at the bottom of the slide, the EPS can be used as bioflocculant to treat wastewater. Okay, here I present you the different steps. We have the wastewater landfill liquid subjected to flocculation using EPS. Different concentration of EPS was used, and after the treatment, the mixture was subjected to settling for 45 minutes of time. Okay. Here I present you a characterization of the sludge used to produce EPS. is activated sludge, and it's possible to wash the sludge or using unwashed sludge. Because you would like to see the difference of the behavior of the two type of sludge, washing versus unwashed sludge. As you can see, when you wash sludge, the concentration of the component decrease, and we expect that that can influence the concentration of EPS. You have to notice that a sludge can be used as carbon source and nutrient also source based of the data that I present you here in this table. Okay, now you can see on this slide we have the EPS concentration versus time. And here it's EPS production while using different type of the pretreatment, hydrolysis pretreatment of sludge, using either calcium hydroxide or sodium hydroxide. As you can see, when using sodium hydroxide, the concentration of EPS is higher than calcium hydroxide using as a pretreatment. So this can be explained by the fact that sodium can be easily react with the sludge and make the sludge very easy to be used with the bacteria during the fermentation. Is the reason for which for sodium hydroxide the result were more important than calcium hydroxide. Also, you make this the tests by using different type of by using crude glycerol and purified glycerol, okay, in the unwashed sludge. So here you use unwashed sludge, and we had crude glycerol because crude glycerol or purified glycerol can be used as a carbon source. So we make the test, and you can see the difference by using purified glycerol and crude glycerol. As you can see, with crude glycerol, the result of EPS production is better than purified glycerol. Why? Because purified glycerol contains less element, less carbon than crude glycerol. Is the reason for which we have more EPS compared to the use of purified glycerol. Also, you use we apply the same test by using wash sludge in the presence of crude glycerol versus purified glycerol. And you can notice that while using crude glycerol, the concentration of EPS is higher than the test while using purified glycerol. This confirms that crude glycerol is benefit to be added in sludge to produce EPS. Now let's see with the application of EPS produced using different type of substrate. Here I present you the characterization of landfill leakages used for while applying EPS. And you can see that the BUD is very high, and ammonia also had a concentration higher than the guideline, the standard. Okay. I would like here to summarize quickly the first result that we obtained while treating landfill leakage using EPS alone or using EPS in combination with ferrous sulfate. As you can see, it's very important to notice that nitrate and nitrate can be easily removed while using SLAM EPS alone compared to ferrous sulfate used in combination with SLAM EPS, because probably ferrous sulfate reacts with SLAM EPS, so that when we combine EPS and SLAM and ferrous sulfate, the result were not good to remove nitrate and nitrate. But when you see the result for COD removal, we can see that the combination of EPS and ferrous sulfate is better. Why? Because ferrous sulfate using alone can be able to precipitate and co-precipitate COD. And when we add simultaneously SLAM EPS, this contributes also to remove COD. And further experiment will be carried out also to see the effect of heavy metal phosphorus removal while using EPS. Now let's talk about the result obtained with water contaminated by landfill leakage. As you can notice here with this table, we have high concentration of turbidity, and also the torque is relatively high, and also the concentration of iron. Okay, here I present you the result in terms of the percentage of the different contaminant removal using EPS alone or using EPS combined with ferrous sulfate. As you can see, when we combine EPS and ferrous sulfate, the result is better compared to the EPS alone. You can see for nitrogen removal, you can reach 30% of the removal, and the iron can be removed up to 85%. So we need to continue to verify the different concentration that can be used to increase the removal rates of the different pollutant mentioned in this table. So for the conclusion, what you can say, you have to notice that EPS was successfully produced by using different types of substrates, such as crude glycerol, sludge, and cooking and waste cooking oil. And during the pretreatment, sodium hydroxide pretreatment is better than the pretreatment using calcium hydroxide. The work established the use of crude EPS as a bioflocculant for the treatment of landfill leakage and water contaminated by landfill leakage. Prime EPS was observed to be better bioflocculant than approved EPS. For some contaminant, removal was higher with a combination of slime EPS and ferrous sulfate. For the future work, a further experience will be carried out to remove the major contaminant to focus on ammonia and nitrogen, which tend to be an issue for electrochemical treatment method. Acetylene solid after EPS production could be used as nutrients media for further EPS production. We need also to optimize some parameters such as pH, time of incubation or fermentation, temperature, chemical coagulant also, and a comparative study between EPS precipitation and chemical coagulant for landfill leakage need to be also carried out during this study. So thank you very much for your attention, and I am here if you have some question. It will be a pleasure for me to give you some answer. Thank you very much.
Thank you, Professor Patrick, for your wonderful talk on EPS. And we came to know across a lot about EPS from you and its potential roles and applications in the landfill leachate treatment. So if there are any questions from the audience, I don't think there are any questions. So thank you, Professor Patrick, once again for joining with us and giving us a wonderful talk on your topic. Thank you.
Okay, thank you very much.
So we'll move ahead with our last speaker of this session, and the invited talk is by Professor Pratibha Karthikeyan Ubli Sami and from USA. So her topic will be current and future trends of bio-waste recycling in United States. She's there. Professor Pratibha, can you hear us?
Hello, good morning. Can you hear me?
Professor, you can hear us?
Yes, I can hear you.
Yeah, we can hear you too. You can just share your screen, Professor, right now.
Can you see my slides?
Yeah, we can see.
Okay. Yeah, thank you. Good morning, everyone. Yeah, so today I'm gonna just give you an outline of what's happening in US, especially the bio waste, and what's the future gonna be look like. And so this topic is, I think, interest to many of you, since most of you working on the waste treatment and waste to energy recovery. And also most of the countries are looking for waste to energy projects and reduce the greenhouse gas emissions. So there is always a link between waste management and greenhouse gas emissions. So I thought this topic would be really a good fit for the audience here in the IFIBiopop 2022. So before I give my presentation, I would like to thank the organizers, and special thanks to Professor Ashok Pandey for giving me this opportunity. So right now I'm working with the Austin Elements Inc. Before getting into my presentation, I would like to just introduce about our company. We are mainly working on the two aspects. One is the lithium battery recycling. So we are using a biological plus chemical process to recover lithium and other precious metals from the waste materials and also from the recycled battery. And another area is mainly on the waste management. So we are providing a support to Arc Energy. Arc Energy is our investor. And last week, Arc Energy was acquired by BP. So that's why we are part of Arc Energy and BP right now. So getting into my presentation, I would like to give you an overview of the waste composition in United States. And so you can see the waste composition, the food waste is the major component of the waste that's going to the landfill. As per the EPA classification, the landfill is nothing but the discrete land area where the waste is dumped and the land is excavated and the waste is dumped and stored. So as of today in United States, you can see that more than 2,700 landfills are operated. So the red dots is open landfills, and which means still it's receiving the waste, whereas the closed ones, which is green dots spread across the United States, are closed landfills. And also the bubble size.
I'm
Yeah,
so sorry,
can you?
Professor Swami. We cannot see your slides moving.
Oh, okay. Maybe I can stop sharing and then share the screen. Can you see my screen right now?
Yeah, we can see the screen. Yeah.
Okay, so maybe I can go. You want to go with the full screen or?
Yeah, that's okay for us if it is moving.
Okay. So yeah, so I was talking about the first slide about the waste composition and distribution in the United States. So you can see that. Give me a minute. So the food waste is the major waste component which is going to landfill. So according to EPA definition, the landfills are nothing but the excavated land area where the waste is filled. So in United States, we have more than 2,700 landfills that you can see spread across the United States, and the red dots mainly the open landfills where the waste is still is dumped, and whereas the closed landfills which is in the green dots, and the bubble size depicts the size of the landfill. So the larger the bubble size, larger the landfill. So we are in Texas, we are in Houston, and we do have number of landfills in Texas. And Texas is the second largest state in the United States, next to Alaska. And so these landfills are receiving more than 300 million tons of waste. So it's receiving 150 million tons of waste every year. So 50% of the waste is recycled through anaerobic digestion or composting or other means, but 50% of the waste out of 300 million tons is going to landfills every year. So this image.
Sorry to interrupt you again, Professor, because we cannot see your slide moving.
Okay, sorry.
We are so sorry.
Can you see my slides now, at least?
We cannot see your screen now.
How about now?
Yeah, you are on the fourth slide, right?
No, I'm on the third and fourth slide. I just moved from third to fourth.
Yeah. We can see it now. Yeah.
Okay, so maybe I can leave it like this so that will be easy. Okay, so this slide mainly talks about the waste generation across the United States, especially from the different states. The red ones are the maximum waste producers, and the green ones are the least waste producers. And this image on the right side, which talks about the methane production capacities of the landfills by different states. The California and Texas were having the large number of landfills, and they are emitting methane. So we know that methane is a greenhouse gas, potent greenhouse gas. So the major concern with the United States EPA is that to reduce the greenhouse gas emission, but at the same time reduce the bio waste which is going to the landfill. So to achieve that, they do have different proposals. But before going into the different proposals that are given by EPA, I would like to also give you some brief introduction about the EPA regulations and how they're moving forward with their regulations and updating their regulations on waste management. So the EPA regulations, based on the 1991 criteria for municipal solid waste landfill, they came up with the landfill design concepts, and then later on they proposed to have a specific liners and final capping to reduce the emissions. And 1996 they set emission standards. So most of the solid waste landfills, municipal solid waste landfill, are classified as subtitle D, whereas hazardous waste landfills are classified as subtitle C, as per the EPA regulations. And as I said before, some of the landfills are collecting the landfill gases, especially for methane, whereas most of the landfills just use the top cover soils to reduce the methane emissions, which means the methane oxidation occurs at the top cover soil, where the bacteria, methanotrophic bacteria, can convert this methane into carbon dioxide. For that, the typical landfill top cover soil composition were also, and specifications were also developed by EPA. So every landfill soil and clay and geomembrane, drainage layer, etc., on the top of the landfills when they going to the closure. So when we think about the methane collections from the landfills, so more than, if the landfill is receiving more than 2.5 million metric tons of waste, or if it is already having 2.5 million metric tons of waste, then it's good site for the LFG collection, especially for energy production. So the EPA created a landfill methane outreach program, and through which number of landfill owners or operators can register and through voluntary program, and they can sell this biogas or landfill gas to the natural gas pipelines. So all these regulations, EPA regulations, and implementations were in practice since 1991 to reduce the greenhouse gas emissions. But right now, the focus is more on reducing the waste, food waste, or any biodegradable or organic waste which is going to landfill as a next approach to reduce the greenhouse gas emission. So by 2030, the United States is aiming to reduce at least 50% of the food waste which is going to the landfill. So the reason why we are linking the greenhouse gas emissions and the waste landfill or bioorganic waste or bio waste dumping into landfill is that we know that as per the COP21, as per the COP21 agreement, every country has to reduce the greenhouse gas emissions to reduce the global temperature rise by less than 2 degrees Celsius. So one of the key elements to achieve that is to reduce the greenhouse gas emissions. So every country is looking for alternative approaches. They're going with the CO2 reduction, as Professor Deepak Pan was explaining. CO2 conversion to value product is on the high priority area for a number of countries, developed and developing country, as well as reducing the greenhouse gas emissions from landfills or for the mining activities or oil refineries is another area of interest to many countries. So the reason why we know that the global warming is one of the major problem that causing a food insecurity, ocean acidification, land use changes, and also the pandemic spread, the corona spread is the best example, and also the loss of biodiversity. So to avoid everything, so the greenhouse gas emission reduction is really, really important. But linking to food waste in United States, so there was some basic study was done by the Natural Defense Council in major cities like Denver, New York, and Nashville. They found that 40% of the US food supply wasted every year are edible. So in that, mainly the fruits and vegetables and prepared foods leftovers were makes up to 60 to 70%. So which means that there are a lot of potential for this food waste to be recycled or used. But the current scenario is that out of 63 million tons of food waste, 50 to 60% is going to the landfill. Only very minimal amount of food waste is digested or used for bio-based material synthesis or composting or animal feed preparations in United States. So as I said before, US EPA as well as the USDA came up with the goal of achieving the food waste going to landfill by 2030, at least 50%. So they came up with the different suggestions. So educating the people, creating a public awareness, improving the data, availability of the data, and also building the food loss and waste infrastructure. So this is where we are mainly focusing on, or any research universities investing a lot of efforts, diverting the food waste to produce value products. So this slide, actually there are three different slides here. So that talks about or give you a picture of how many food waste digesters are distributed across the United States. So they were categorized under three different category. One is the digester co-digestion of food waste in a wastewater recovery facility. So there are 1,265 wastewater sludge digestion facilities, and roughly 20% of them are treating the food waste. And also there are 200.
Hello. Professor, we cannot hear you. Are you there? Hello. Yeah, Professor Karthikeyan, we cannot hear you. Hello. Professor Karthikeyan. Yeah, I think there is an issue of audio from his end. Yeah. Professor Karthikeyan, can you hear us? Professor Karthikeyan? I think there is some problem at his end. Neither his slides are moving.
Main output.
Yeah, Professor Karthikeyan, can you hear us? Hello?
Hello.
Yeah, we can hear you now. I
Okay.
think there was an
Yeah.
issue.
Sorry. Okay.
Professor Karthikeyan, we will just request you to cut short your presentation because we are running out of time. Thank you.
Okay. Okay. Sure. So yeah, based on the scenario development and techno-economic calculations, I can quickly go through these three different scenarios. So the scenario one, that's composting and anaerobic digestion for methane production. So that's going to produce close to $350 million per year. Whereas if you produce hydrogen, it's going to be a little bit higher, hydrogen plus composting. But if it is a combination of composting, hydrogen, and animal feed preparation, there will be a little more higher capital and revenue. So in our industry, we are developing a hydrogen and methane production system, like Hythane system. So where we treat the food waste and we produce the leachate, and leachate goes for hydrogen production, and followed by that the BFA from the fermentation process goes for the methane production. So we did techno-economic calculation. So this will be a pilot scale operation that's going to go into the landfill. So the Archaea Energy own the biggest or largest landfill in the United States, which is in Pennsylvania state. So this pilot plant is going to be at the Pennsylvania landfill, where the food waste will be treated for hydrogen and methane production. So based on the 1,000 metric tons of food waste treatment capacity, so this is our capex calculation, and the total capex was calculated as close to $335,000 plus additional charges, whereas OPEX will be close to 180. That includes the chemicals and electricity and manpower cost. So based on the product's revenue is going to be, the lower case is going to be 158,000 and the upper case is going to be 270,000. So in either case, we will make some profit out of it. So larger the plant size, and better the revenue going to be. So to complete the presentation, so we had three scenarios. The fourth scenario is what we are working right now, but we will be also eventually working on scenario 3 that's going to be more profitable in converting the bio waste into value products. And there are a number of waste management companies in the United States. These are the top players. And we are closely working with Archaea Energy and also partly working with Waste Management Republic Services. They are the largest landfill owners in the United States. So in summary, so definitely the food waste current practices is not very appealing in the United States. Most of them are going to the landfill. So we propose to develop an integrated biorefinery concept, and we hypothesized different strategy, and we are testing Hythane production in a two-stage system, and the pilot scale operation will be soon in a big run landfill, which is in Pennsylvania state. So the future of the food waste or bio waste management in US will be more towards the energy recovery and value addition. So thank you. And as I said before, my special thanks to Professor Ashok Pandey and Professor DJ Lee and Dr. Anil Kumar Patel.
Thank you so much, Professor Karthikeyan, for such an enlightening talk on bio-waste management and bio-waste in USA. I think management of bio-waste is a very huge problem around the globe, and we think in future, in coming years, we'll be taking stringent steps and research so as to reduce it and use it in efficient way so as for sustainable development also. Thank you, Professor Karthikeyan, for giving us your talk. So we'll end the session 2 here, and now we will proceed towards the lunch. So the lunch timing is from 12 to 1 o'clock, and sidewise we'll also be having the poster session. It will be from 12 o'clock to 2 o'clock, and we will meet again for session C, 3C at 2 o'clock sharp. So I request everyone to be to join us for session C, 3C at 2 o'clock. So thank you very much.
Yeah, thanks everyone.
Thank you. very good afternoon to everybody. So shortly we are going to start with the session 3. So I request everybody to join us.
Good afternoon, Dr. Vishal Sharma. Can you hear me?
Professor Eldon Rene, we can hear you. So we'll
Okay,
just
okay.
start in a minute. Thank you.
Okay.
A very good afternoon once again to everyone. So I am Vishal Sharma. I welcome you all to the session 3 of IBA 22 conference being held in National Kaohsiung University of Science and Technology, Taiwan. So in our series of inviter lectures, so our first inviter lecture or inviter talk is from Professor Eldon R. Rene from Netherlands. So he has joined us online from Netherlands. So his inviter talk is on the topic application of photo sequencing batch reactors for wastewater treatment and resource recovery experiences from the Pavitra Ganga project. So this title itself sounds quite interesting to us. So over to you, Professor Eldon, for your talk. Thank you.
Yeah. Thank you, Dr. Vishal, for your nice introduction. And I would like to thank the organizers for giving me the opportunity to present the topic that we are working back in the Netherlands together with Indian partners on a Pavitra Ganga project. So can you see my slide moving? Dr. Vishal, can you see my slides?
Yes, Professor, we can see.
And it's moving, isn't it?
Yes.
Okay, good. Yeah. So this is a project that we are doing together in collaboration with the Indian partners, basically from IIT Delhi and also IIT Kanpur. And it's a 3-year fully funded project from the European Union and also from the Department of Science and Technology, where we have we have 2 demonstration sites, one in Kanpur and one in Delhi. So I'm going to present the work that we did as a part of the work in Delhi, because we have a drain complex which is treating the wastewater that is coming from the drain. And at the same time, what we also tried to do was to simulate the conditions of the drain in batch systems at our laboratory. So briefly, I would like to tell a bit about this project. This project is it has around 22 partners from both the European Union and also from India. And the main idea of this project is it's not only wastewater treatment, but it's also on water reuse and also identifying opportunities for resource recovery. And there is also, this is all the technological components, but we also have a governance component as well as a policy component with a lot of stakeholders from India involved. That also includes the community of farmers. So basically, what we are doing from IIT Delft in the Netherlands is we work together with IIT Delhi to develop a photo-activated sludge system. It's basically a raceway pond that contains both bacteria and algal consortium. So the whole idea is to cultivate a mixed consortium of algae and bacteria, and the bacterial species that we chose here is basically activated sludge, which contains a lot of nitrifiers, which was collected from a wastewater treatment plant located in Delhi. And the idea was to remove a lot of pollutants from the Barapula drain. And the Barapula drain itself is just domestic wastewater, sewage, and a lot of other things that are just flowing. And it also has seasonal fluctuations depending on the rainfall, the summer season, the rainfall season. And basically for the algal consortium, it was a mixed algal consortium. We did not go for any specific consortium. So this photo-activated sludge system, it differs a little bit different from the pond system because it optimizes the growth of both the mixed consortium as well as also the nitrifiers as well as the algal population. That's mainly because of the dark and light cycles. And this is the photograph of the 1,500 liter capacity raceway pond that we had installed here. So this system at the moment is under it's under pilot scale evaluation, and we are directly feeding, because actually here in this side you can see the drain side, the drain that is flowing from the drain. We collect the wastewater, we take it into a settling tank first, and from the settling tank we settle all the settleable solids, and after which the clarified liquid is sent into this photo-activated sludge system. And at the moment I'm not showing you the results from the pilot scale, but instead I would like to tell a little bit about the whole rationale behind this approach is not only treating wastewater but also to enhance the lipid productivity using the microalgae and bacterial consortium. So we call this reactor as a photo sequencing batch reactor. The reason for calling it as a photo sequencing reactor is it works exactly the same as a sequencing batch reactor with the fill, settle, the fill, react, settle, and the decant phase, where what we tried to do was we also at the same time we did 2 cycles of operation per day. One is a dark cycle and one is a light cycle. So that is the reason why we shifted the name from photo activated sludge to a photo sequencing batch reactor. So in this case, the specific objectives was to test the technical feasibility of the survival of the fattest mechanism to enhance lipid productivity in the bioreactor using COD and a TIC rich. TIC is nothing but the total inorganic carbon, which can be consumed by the algal species. And then to also compare the performance of 2 bioreactors configurations under the survival of the fattest mechanism. So what we tried to do here was the methodology that I would like to say is it's a bioflow reactor. It's nothing but like, it looks very similar to a fermenter, a 2.5 liter capacity with an operating volume of 2 liters. And we had 2 cycles. One is the light cycle of 10 hours and the dark cycle of 14 hours. And we supplied the influent at 35 ml per minute. HRT was 2 days. And in this case, it was a mixed algal consortium, as you can see, with 5 different species of algae. And I would like to tell the difference between the photo sequencing batch reactor number 1 and number 2. It's nothing but the COD to nitrogen ratio were different. Here you can see for an ideal case, we had 1 COD, but for the second reactor, it was 50:50 ratio of COD and nitrogen. And this was not a real wastewater. It was a synthetic wastewater that was prepared using sodium acetate and then ammonium chloride. And we operated this whole system for approximately 120 days. And for the algal species, we took the water samples from the canal of Delft, and the microalgal species were bioaugmented with the room temperature, and we didn't have much of sunlight there, so we had to go for both natural as well as the artificial light. And we call these two systems, the ideal case and the other one, This also simulated a little bit of industrial case, because in a synthetic brewery effluent, you have a lot of COD, whereas for a liquid digestate, you have a lot of nitrogen. So that is why we call it as a mixed synthetic brewery wastewater and a liquid digestate. So we also added these microalgal species on different days to these two bioreactors. So this is the bioflow controller. This, as I had mentioned to you, it's a modified fermenter that is now operating as a photo sequencing batch reactor, and it is controlled with this bioflow controller for all the process parameters, and we also have online systems to monitor the different parameters over the time of the reaction. And here you can see the different phases of operation: the settling phase, the decant phase, the reaction phase. So as I had told you before, we did it with two different cycles of operation, the dark and the light cycles. And it's a similar way with PSBR2. We also did a similar operational sequence. And now coming to the lipid measurements, yeah, it was a bit tricky because we didn't have much of biomass to do the lipid measurements, because these were conventional methods, the Sochel hexane method and the chloroform methanol method, which required a substantial amount of algal biomass to measure the lipid productivity. But in any case, we monitored that not on a daily basis, but it was only periodically monitored. So the results, it was basically with respect to the color intensity. You can see from days 1 until day 63, as well as also from day 15 to day 47, you can see a good growth of the algal species. It's basically, this is microalgal growth. And here you can also see the temperature, pH, and oxygen profiles in the PSBR reactor number 1. And we found that there was also the dominance of heterotrophic bacteria, the nitrifying bacteria. And when we also, after the COD supply was stopped, we did not have the organic carbon, but instead we went for the total inorganic carbon addition on the day 28, because we wanted to simulate the growth of the algal system. And in this case, we were not monitoring how much amount of CO2 was consumed, but instead we were only monitoring the TIC, that is in the liquid phase. And in the PSBR reactor number 1, we also we found an increase in the nitrite and nitrate concentration due to the presence of the nitrifiers. And then we wanted to, because many times the nitrifiers outgrew the algal biomass. So for that reason, we also had to do a little bit of troubleshooting, such as adding the nitrification inhibitors. So similarly, you can see here, this is the profile of COD and TOC, TIC. In the case of COD, you can see for every cycle of operation, from an initial concentration of 80 or 70, it gradually decreased. But in all the experiments, surprisingly, we were not able to see the complete removal of COD, except in very few cases. Probably, I have the impression that it was the cycle length was not enough, or maybe the concentrations were high, or the C/N ratio was also not under the optimal conditions. But in the case of the TIC, also you can see there was only a gradual decline over the different phases of light and the dark cycles. Similarly, for PSBR2, the PSBR2 reactor had 50% of COD and 50% of nitrogen. And here also we were able to see around 2 milligram per liter per hour removal of COD. Then with respect to TOC and TIC, they were really less, 0.3 and 0.7 milligram per liter hour. And the average TIC production during the dark period was 0.3 milligram per liter per hour. And with respect to the nitrogen profile, you can see that the ammonium and total nitrogen removal rates were 1.2 and 0.9, and the maximum nitrate was reached on the 16th day of operation. So what you can see here is the different peaks that is there, that is mainly because we also, as I mentioned, we added the nitrogen for the nights during the second cycle of operation. That is why you see this this peak. With respect to the nitrate concentration also reached a maximum of 1.5 milligram per liter on the 21st day of operation. And with respect to the lipid content and the productivity, it was around 54.3% and 4.1 milligram per liter per day, respectively, for the PSBR1, whereas for the PSBR2, which had 50% of nitrogen and 50% of COD, it was only 18.6 and 3.6 milligram per liter. So under this condition, what I would suspect that I would say is that the PSBR reactor number 1, which was operating in 2 different cycles with different ratios of COD and nitrogen, I think it performs really well in terms of enhanced lipid productivity. So I would like to summarize all the data that we obtained in the form of one nice table. We could see that in PSBR1, we obtained the maximum COD removal rate, and also with respect to the removal profile of TOC or TIC or ammonium, it was all highest in PSBR1. And with respect to the lipid content, it was also the highest in the PSBR reactor number 1 compared to the PSBR number 2. So here, the nutrient limitation did not favor the biomass growth. So that was one of the hypotheses that we had in mind, that when we are going to do a starvation of nitrogen, probably there might be some inducing mechanism where the lipid productivity would increase, but that necessarily did not favor the biomass growth. And the biomass productivity and the chlorophyll were low in the PSBR1. And as I also mentioned before, there was always a residual of these carbon sources that got accumulated from each cycle, because not all the carbon was completely withdrawn, because during the settle phase, we still had the microorganisms, and there was always a residual carbon and nitrogen left. So when the second phase came into, when the second cycle was fed, it always contributed to an addition of this carbon and nitrogen. So that is also one of the reasons that we were not able to achieve 100% removal of any of these pollutants. So with this, with these results, I would like to conclude my presentation. And if you have any questions, I'll be very happy to answer to the questions. Yeah, thank you.
Thank you, Professor Rene, for your detailed talk. It was really motivating, and I think everybody should be, yeah. So I think we can take questions now. So we have a question.
Yeah.
Hello, Professor. You've done a great work, but I still have a very small thing to ask. I noticed that you supplied ammonium during the night and carbon during the day, and the night phase was longer, like 14 hours. So do you think the ammonium absorption by algal part would be disturbed by that? Because ammonium as a nitrogen source uptake requires light in algal species. So wouldn't it affect the nitrogen utilization by algae? Because I also saw that there was a lot of nitrifying activity.
Yeah. Okay. So, thank you very much for your nice question.
Thank you.
The reason for we had a in our lab, we are not supposed to work after 8 p.m. So for the collection of the samples and everything, we kept the day cycle less than the night, which is not the condition, which is not the ideal situation. For example, in India, we have around 12 hours of sunlight days from 6 to 6 p.m. So this was one of the hindrance for us, and the idea of having this because the problem with the nitrifiers is the nitrifiers sometimes outcompeted the algal biomass, because they were also, because that it came from the activated sludge, and the bacteria present in the activated sludge also contributed to COD removal.
Yes.
But you are totally right, because when you give so much amount of time, the nitrogen would possibly also get absorbed. Yeah, you are right. Okay.
Yes, yes, yes. Thank you.
But we did not check that. But I think it would be ideal to take some of these samples outside, and to do a bit of adsorption tests as well. Yeah.
And I think uh, bacteria would outcompete microalgae in organic carbon consumption, but when it comes to nitrate, I think algae can any day outcompete bacteria given the proper elimination condition. It's my humble opinion.
Yeah.
Thank you.
Yeah. No, you're totally right, and that is why I also mentioned about this carbon to COD to nitrogen ratio as well. No?
Thank you, Professor Rene. So thank you for your presentation. Thank you.
Yeah, thank you so much. Yeah, thank you.
So our next invited speaker is Professor Giorgio Manina from Italy. Are you there? Yeah, yeah. So
yes.
Can you hear us, Professor?
Yes. Can I share my screen?
Yeah, sure, Professor. So Professor Giorgio will be talking on resource recovery from wastewater, new insights from the case study of Palermo University within wider uptake project. So Professor, it's over to you. Yeah. Yeah, we can see your slides.
Okay, perfect.
Yeah.
Okay, so thank you and good day, everybody. What I'm going to present is some insight from the case study of Palermo University, which is the first water resource recovery within a campus of a university. So first of all, let's start with a brief introduction. As you know, historical goal of wastewater treatment plant basically were to protect the environment towards the pollution, and also to protect the citizen from the hygiene, so for problem related to the risks of wastewater. And looking at the wastewater treatment plant, we can, of course, distinguish these two main flux. One is the treated water, and the second one is the sewage sludge. And the sewage sludge, the wasted sewage sludge, is going to increase, especially because we have two factors. One is the building or revamping of new wastewater treatment plant, and also the different limits are becoming stricter, so the wastewater treatment plant is performing always higher, and this basically are causing an increase of this solid waste, and this is becoming a challenge, a problem for finding a solution where to dispose this sludge. Today we are assisting to a new paradigms in terms of wastewater treatment. So we are moving towards the circular economy. So basically we are moving from this linear system where we have we take a source and then we produce a product, and then we dispose of this used product. In contraposition to this scheme, we have the well-known circular economy, where basically we replace the goods and product that we produce in order to minimize what we dispose of into the environment, and this of course is more sustainable. So the point is that wastewater is an issue or an opportunity to deal with. So this sludge and this material that we want to dispose of can be recovered. An answer to this question is given by this very insightful project, which I will present some piece of the research more related to bioplastic. And according to this project, basically we want to create this circular economy system, but there are some barriers. And we want this barrier not just technological, but are also legislative, organizational, administrative. And for achieving this goal, we are trying to create an industrial symbiosis, because it's not just a matter to recover the material, but the point is what we can do with this material is any market. So we have to facilitate the involved engagement, also the society, and also create a structure where this material, this recovered material, can be effectively used. Otherwise, it's just a speculation. We start storing this recovered material. So to do that, the project basically consider what is called water smart solutions, which basically recall the concept of water smart society, where this is a society where the value of the water has a value, and the environment has to be protected. And as I said, we want to break these barriers for putting the concept of circular economy in practice, so to create a market. And for doing that, we need also to create a new governance and business model for this circular economy. This is a paper that where you can have a look more in details about this project. So today we are assisting to severe problem related to the plastic. So these are basically contaminated several environments, several feeding environment from the water and so on. And when we look at the bioplastic, we can also find this interesting polymer, which is the polyhydroxyalkanoates, which basically are reported some details regarding the properties can replace the actual quite spread plastic that comes from petroleum. However, we have some challenge related to the price, which is still very high, and which basically is the main obstacle for having a wider application in the market. So it's one may ask why these polymers are considered one of the most important alternative to the petroleum. So basically, the polyhydroxyalkanoates, here there is a structure showing you how is organized, and we have several microbial community who take part to the wastewater process that can produce and store this polymer inside the cell. So considering mixed culture bacteria, we can distinguish four main steps for the production of this polymer. So basically we have, first of all, the production of volatile fat acid by fermentation from the sewage sludge. Then we have the selection, so the production we needed to select the bacteria that are more strong in the production of this polymer, and so this is a sort of selection of the bacteria. And when is selected, we can start the accumulation inside the cell for finally extracting from the cell, producing this polymer. So as I said, we can have different feedstock for organic COD for producing volatile fat acid, and among these we can have the optimization of the operational condition in order to produce more volatile fat acid, which are needed for the bacteria to grow and then start storing these polyhydroxyalkanoates or PHA. And this is in this graph is reported the different rates in terms of feedstock that we can achieve. You can see also that we have from going from organic food municipal solid waste to also using sewage sludge, which is pre-treated by thermal treatment. But in general, we can say that that using sewage sludge can be considered as a challenge because of the contents of volatile fat acid and in general COD that we have. have. So just a few words about this bacteria. As I said, this bacteria basically accumulate polydrosalcanoates after selection of the best bacteria which can do this job. So basically, how is possible? Because according to the process, we induce a sort of stress in the bacteria by alternating a phase of feast, and then where we produce carbon, and then famine, so where we do not provide substrate. And this basically allow them to have this this alternation of feast and famine, allow to create bacteria that basically are trained for storing this PHA. We can distinguish in the biomass selection these two streams, aerobic dynamic feeding and anaerobic aerobic selection. And in aerobic dynamic feeding, we can have different steps, as such as the SBR reactor, where we can have high PHA storage yield and high energy consumption. And for the anaerobic aerobic selection, we can use, instead of the carbon, for instance, the nitratation, so nitrate source for feeding, and this can be convenient from the energetic point of view, so again from the sustainable point of view. So we can replace the oxygen to the nitrate for as a electron donor. And this can be done, for instance, by using this reactor, where you can control the oxygen in order to provide the best condition for feast and famine, as you can see in this graph, which basically represent a cycle. And you can notice that you have a first step where you have the feast, so the bacteria are fed with carbon, and then you have an alternance of famine, where basically the carbon decrease and the bacteria start to be without any carbon, external carbon. Or you can use this second scheme, where, as I said, you can provide, instead of oxygen, nitrate, and then this is taken as an electron acceptor, and this can be convenient in terms of course, energy. So you can save emissions in terms of indirect emission. So the goal is to increase the amount of PHA stored inside the cell. And how we can do this? Basically by providing these alternates and then monitoring the DO before this shift up famine substrate is shift again. So after selecting, we can monitor the pattern of DO, and when DO is decreasing, then we can provide some carbon, and so we can basically have only this continuous pulse cell feast with no famine, so only feast by providing the carbon, and then we can store maximum amount of PHA inside the cell, and then we need to distract the cell to take these polydrosalcanoates inside the cell. This basically opens some questions related to the purity of these destruction methods. We use this protocol, which is based on these steps for destruction, by trying to use some solvent which can be environmental friendly, so which can be in harmony with the environment. We use chlorinated solvent, alcohol, surfactant based solution. So these are possibility that we can use, but again we have to take into account the fact that the process should be as trying to limit the pollution, try to limit substances that are nocive for the environment. We also are trying to scale up this process, and we have these three systems where we apply this process. One is basically the contents of my presentation, which is, as I said at the beginning, the case study of Palermo University, which basically we build up this water resource recovery system. But we have also other two wastewater, one in Marineo and one in Corleone. I will spend a few words about Palermo campus. So this is a map of part of our campus, which is nice, is around 10 hectares, and you can see two lines, one in yellow and the other one in blue. So basically the one in yellow represent the pumping station. So where we basically had the capture of the sewage, the wastewater, sorry, which is basically produced by canteen and dormitory and apartment inside the campus. And then we go in this area where we have the treatment with a plant hall, where we have some treatments, and then with the blue line we distribute the irrigation, the treated water, and also we replace some materials in order to have a circular economy concept. This is the overall schemes represented with the different flux from the raw wastewater, treated water and sewage sludge that is coming from the treatment of the water, and we produce also fertilizer at low release. These are a few photographs showing you the pilot plants hall and also the new lab, the water resource recovery lab, which has been built inside the campus for the analysis of the different parameters for the monitoring studies. This is the polydroxyalkanonate pilot plants streams. You can see that we have several reactors with a fermenter, and of course we have also pumps and electricity engine PLC for allowing the working operation of the system. So there is, as you can see, a fermenter for the production of polydroxyalkanonates, which for the production of volatile fat acid, which are then separated by using an hollow fiber membrane, and then these VFA are used jointly with the nitritation SBR, which is used in the scheme without oxygen for the selection reactor, selection SBR, which is in operation in this scheme according to another membrane where we can separate the permeate, and we can obtain biomass that is can store, is trained to store PHA. Then the PHA is accumulated, is enrichment reactor where we basically carry out the test for increasing the degree of the amount of PHA. This is a paper describing our plant. As I said, we have also other two case studies, one in Corleone and one in Marineo, and these basically are conventional activated sludge wastewater treatment plant, and described in this paper. You can have a look if you want to know more. And inside we build a shed where we have an upscale of these polydroxyalkanonates pilot plants, treating this time the wastewater, sewage sludge and so on produced by this wastewater treatment plant. A few words about the activities that we have carried out so far. These are, we consider different schemes. Indeed, these results are related to these schemes where we have the fermenter and then the SBR. In this case, we used synthetic substrate because then we are comparing with the real sewage sludge, so real wastewater, in order to see the yield of polydroxyalkanonates. These are some tests that batch tests that we carry out in order to understand the influence of volatile solids and the PHA, and we found the best ratio in terms, you can see it tests T1, T6, the best ratio in terms of volatile fat acid, and also the the PHA. We carry out also the metagenomic analysis for identifying the bacteria that are participating to this process, and then we were able to monitor the pattern or volatile fat acid and COD, so the ratio, because our aim is to maximize, of course, the production of VFA, which will be the carbon source for the bacteria. This is the operation, some results led to the operation of the fermenter, where we try to optimize the headspace without providing any air, any liquid, gas, sorry, for minimizing the effect of the headspace, and we tested how this headspace influence the production of VFA. We also run 3 different organic loading rate. You can see from 0.8, 1.3 and 1.8, where we want to maximize, again, as a function of the OLR, we would like to maximize the VFA by keeping the plant in good efficiency in terms of removal capacity. These are the results of the performance in terms of carbon, ammonia, and orthophosphate, and we were able to identify the best conditions for the organic loading rate. We also carry out some microscopic analysis to see how the polymer is accumulated inside the cell, and we identify the best condition for maximizing the contents of PHA inside the cell. This is the accumulation station that have been built inside our lab in order to have the accumulation, so the enrichment of the bacteria, which follow is basically managed by an automatic control software, and this software allow again to provide also a possibility to scale up in industrial level. These are the results that have been derived so far, with some tests aimed to identify the best conditions in terms of PHA production. And again, in this case, you can see for text 6 with an OLR of 1.8, we got the maximum yield of polydosylcarbonates. These are finally the results that have been derived of this polymer, which include the recovery and the purity of the PHA. The purity, depending what you need to do, can be higher or lower, so this can be also an option for the final usage. So this is are just a picture about the extracted PHA. And finally, just before concluding, these are the other layout that we are going to test using, as I said, the nitratation SBR, and then also these other schemes where basically we are introducing the all training streams, which include also the membrane for the separation of the permeate from the main streams. So I would like to thank all of you for listening my presentation, and looking forward to questions. Thank you.
Thank you, Professor Giorgio, for your detailed talk. And the session is open for any questions. I don't think there are any questions. So thank you once again, Professor Giorgio, for your talk. Thank you.
Thank you.
Now we will move to the next invited lecture from Hao Yong from Singapore. He will be presenting online, and his talk will be on enhanced treatment performance and fouling control in novel vibrating anaerobic membrane bioreactor towards energy neutral domestic wastewater treatment. So, Professor, please.
All right, good afternoon, everybody. First of all, I'd like to thank Professor Kandi and Professor Tong for the invitation. Now, today I'm going to talk about the novel vibrating anaerobic membrane bioreactors that can achieve towards energy neutral for domestic wastewater treatment. Now, just now, Professor Georgia has mentioned about the circular economy issues. As we know very well, resources is limited, and all the natural resources, including energy price, is shooting up, and the impact of climate change has been experienced in many parts of the world, especially in terms of water scarcity. So, as environmental or water engineers, we look at how we can recover resources from wastewater. As we know very well, all material used or consumed domestically or through industrial productions will end up in either the solid waste or wastewater. While there have been extensive efforts vested in waste segregation and recycling of solid waste, similarly, water reuse, reclamation of resources, recovery has received increasing attention. Wastewater could provide these invaluable resources in meeting the growing demand for fresh water and other raw materials, including PHA that just now Professor Georgia has mentioned. So wastewater is a variable resource in a world where water is finite and demand is growing. This is said by Guy Ryder, the chair of UN Water and Director General of the International Labour Organization. Now, this diagram here shows how the water reuse is typically done. For example, in Singapore, where we have water recycling through the production of Singapore New Water. Now, in the heart of this whole process is the biological treatment process, and in Singapore, we use a membrane bioreactor. Now, one of the major challenges in wastewater treatment or water reuse is the energy consumption, right? So, in this case, you'll find that the membrane bioreactor is an aerobic process. It will consume high energy due to aeration and pumping, right? So, as we know very well, there should be effort. There are much research ongoing trying to reduce the energy consumption in aerobic wastewater treatment. Now, so in conventional biological wastewater treatment plant, electricity alone will consume from 25 to 40% of your annual operating budget, and that primarily due to the electric consumption alone. So, of course, there has been increasing interest in exploring anaerobic processes for wastewater treatment. And anaerobic process, which was developed since the 1960s, has been proven as an attractive technology for the pre-treatment or even treatment of high-strength wastewater and for sludge management. In recent years, there are much focus has been put into generating high-value products from this process. Of course, we know very well biogas in the form of methane and hydrogen may be recovered from anaerobic process. Both such gases may be used to generate energy to offset requirement from conventional wastewater treatment process. So for biogas, which has a mixture of methane up to about 70%, carbon dioxide and trace of other gases such as nitrogen or hydrogen, generally can be recovered in the form of energy from wastewater, right? And then this biogas can be used for electricity generation or for heat production. Now, for wastewater treatment, there has been increasing interest looking at anaerobic membrane bioreactor. Okay, and when you talk about membrane bioreactor, basically you are using the membrane to separate the bacteria and the treated water. Now, through this process, you produce biogas like the typical anaerobic process, where you can use this for power generation or even for other for heating, right? Now, the product of the anaerobic MBR permeate is effluent that is free of bacteria, but unfortunately, it has a high concentration of nutrient like nitrogen, phosphorus. This wastewater can potentially apply for agriculture, irrigation, or even for microalgae cultivation. Now, the other approach people look at is to look at the nitrogen phosphorus recovery through adsorption or other methods. Now, the digestate can, of course, be utilized as a fertilizer if as long as there's no other heavy pollutant like heavy metals. Now, if we look at this is a paper that was published in 2014, looking at how does anaerobic MBR versus other technology like anaerobic food digestion of waste versus activated sludge with anaerobic digestion. So on this axis here is increased global warming potential versus energy consuming. Downward is back, of course, to the top right is the green area, which is advantageous in terms of carbon offsetting and energy recovery. So you can see that the current anaerobic MBR is still not attractive compared to the high rate activated sludge with anaerobic digestion. All right, and this is the potential of future anaerobic membrane bioreactor. Now, so where is the issues here? All right, the issues here, you can see that this table here shows you the different in terms of energy consumption due to aeration. In this case, for MBR is due to membrane spudging. So for anaerobic MBR for middle strength, high strength, you can see that membrane spudging using biogas is the major energy consumption, although you have biogas production. Now, because of that make the over energy not so attractive. All right, so the key challenge here for us is that can we reduce the energy consumption due to membrane spudging? Is there any other alternatives besides using biogas as spudging like the conventional aerobic membrane bioreactor? That's the main reason why it motivates us to attempt to explore vibrating anaerobic MBR versus biogas spudging anaerobic MBR. So in this study, basically what we have found earlier is that membrane vibration could save up to 78.5% energy compared to air scouring aerobic MBR. All right. So it has been demonstrated in our earlier study showing that membrane vibration is much more energy saving compared to the conventional air scouring MBR. Now with that, we explore applying the same concept into anaerobic membrane bioreactor. So in diagram on the left here show the lab scale reactors where we have the main anaerobic reactors with the effluent with the mixed liquor pumped towards a membrane separation tank, and in the lab is a vibrating ceramic membrane. All right, and on the right is the conventional biogas spudging anaerobic membrane bioreactors. So this is a picture of how the reactor look like. Now, so in this experiments, we split the whole process into 4 different phases. Phase 1 is the startup phase, and phase 0 is a startup. Phase 1, you can see that we run over almost 100 over days, followed by phase 2 another 50 plus days, and then phase 3 is another about 20 plus days. So what's the difference between this phase 0 to phase 3? So phase 0 is startup phase. Now then phase 1 is a high shear stress where we apply much higher rotation for the vibrating MBR and also for the bar scouring anaerobic MBR higher air spudging, bar gas spudging, and then phase 2 is lower and the lowest is at phase 3. Now for first step, what we do experimentally is to determine the critical flux, okay, for the different air spudging phases. So you can see that we control why we choose 120 RPM, 1.5 LM liter per minute. Okay, it's very much due to so that they have a pretty much similar critical flux. So on the left here is 1.5 liter per minute of bar gas spudging and 120 RPM. So we make sure that they are comparable in terms of critical flux. Now the membrane we use in this study is ceramic membrane flat sheet, pore size of about 0.1 micrometer in terms of nominal pore size, and working volume is 1.2 liters, HRT 12 hours, SRT of 30 days, and temperature is ambient temperature. And we run the system with a flux of 12 LMH. Now, let me show the performance of the two anaerobic bar reactors. So you can see here, this is a real domestic wastewater with a total COD of about 370. There are slight variation over the three different phases, but very much about 340 to 370 milligram per liter of total COD. It's a domestic wastewater, so ammonia is about 45. The primary, most of the nitrogen is into ammonia, all right? And then you will find that in terms of COD removal after treatment, the permeate we get about range from 37 all the way to about 41 milligram per liter. So we achieve about 89% of organic removal, and there's not very much different, okay, between vibrating versus the bar scouring. But what you can see is actually consistently over the three phases, there's slightly about 1% more organic removal by the vibrating anaerobic MBR. Now, in terms of MLVSS is about 7 gram per liter running at this operating condition. Now, so down here on this three diagram here, I'm just showing you the COD in terms of the feed, and then the removal efficiency. You can see almost about 90% removal efficiency. Now, interestingly, for the gaseous methane production, because in this bar reactor system, we recover methane by the natural gaseous emission in the main bar reactor and also the membrane bar reactor, and we monitor the overall gas production. So what we can see here is that for the vibrating anaerobic MBR, it has a slightly higher in terms of gaseous yield per liter, gaseous in terms of liter per gram of COD removed. Okay, so you can see that consistently it is higher, all right, higher compared to the gas spudging anaerobic MBR. Now, what we found here is that in terms of the yield, we get about 0.2, okay, compared to theoretically 0.35. Okay, so the reason is because most 0.35 include the dissolved methane. So you can see that there's substantial amount of methane is in the dissolved form. All right. Now, so you can see that dissolved methane is in terms of ppm, substantial amount is in the dissolved form. I would say even oversaturated compared to the Henry's law calculation. But you can see that the vibrating anaerobic MBR consistently show lower dissolved methane compared to the bar gas spudging. And then oversaturation by about 2 to 2.5 times. Okay, 2 for the vibrating anaerobic MBR. Now, when we do a computation on the COD balance, what we can find is that basically the dissolved and the gaseous will account for about 65% for the vibrating anaerobic MBR and 64% for the bar gas spudging anaerobic MBR. And then when we compute the total bar gas yield, is get about 0.3 liter per gram of COD removal. So this is pretty much close to the theoretical value of 0.35. All right. So based on this study, we found that the vibrating anaerobic MBR had more bar gas yield, all right, compared to the bar gas spudging, especially when we talk about the gaseous yield. All right. So less. If we eventually want to recover all the methane, the post-processing to extract the dissolved methane will be lower for the vibrating anaerobic MBR. Now, more importantly here is the fouling control, okay? So down here on the diagram on the left, the top is the vibrating anaerobic MBR and the bottom is the bar spudging anaerobic MBR. So you can see that in phase 0, during the control phase, you find that the TMP rise, okay, vibrating is the startup phase. Okay, only 2 cycles of fouling. All right, compared to the bar gas sparging, there are so many of time, because normally in our MBR operation we run at a constant flux condition, and when the membrane foul, the TMP will increase. Okay, so once it hit about 30 kilopascal, we will stop the system for chemical cleaning of the membrane. So having a very rapid short duration of increase to 30 kPa means the membrane foul faster. All right, so consistently we can see that throughout the 3 phases, the vibrating is more efficient in terms of membrane fouling control. Okay, now if you compare across the phase, like phase 1 is the most rigorous fouling on the highest shear stress, followed by middle and lowest. You can see that high shear stress is more effective. Okay, more effective in membrane fouling control. And then and then from here, the right table, we compute the TMP rise per day for the bar sparging versus the vibrating anaerobic MBR. So this is basically computing the result from the left into a numerical value in terms of kilopascal rise per day. So it's basically demonstrate the same thing. Bar gas sparging increase faster, and then of course phase 3 is faster because of the lowest shear force provided. Okay. Now next is that we try to understand what actually contributed to this fouling. All right, so we look at fouling sources. This is for the mixed liquor particle size, bacterial size, and what we found here is that the macro size in terms of micrometer is pretty much similar, but interestingly, when we look at the micro particles like nanometer size, you can see that as your phase 3, phase 1, which has a highest shear force, for the bar gas sparging, there is high percentage of low small molecular particle size of, for in this case, about 50 to 60 nanometer. All right, because the shear force is so high by the bar gas sparging that you actually break up the bar flux and create all these colloidal small particles. Okay, but if you look at the vibrating, all the small particles are very much consistent. You don't see a peak. All right, but as you reduce your shear stress for the bar gas sparging, particle size, small particle size increase. All right, so bear in mind there's all these small particles. Now, when you look at the mixed liquor dissolved organic carbon, for the bar gas sparging, relative compared to vibrating, you can see that it is higher for both dissolved organic, all right, in terms of in the SMP, in the EPS consistently. Now, but if you look at for the bar sparging by itself, as you drop the shear force, the DOC actually drop, okay? But for the vibrating is pretty much constant, all right? Likewise for the EPS, all right? So what does that mean? It means that actually this high shear force, although it's very good, it is very good in fouling control, it's actually shear a lot of this flux and resulted in the higher dissolved organic carbon in the SMP and the EPS. And then we do go further to look at the polysaccharide versus the protein. We see a very similar trend, like the dissolved organic carbon. So the point here that I'm saying is that high shear force is very good, okay? And if you compare the DOC in the mixed liquor, the polysaccharide, the protein in the mixed liquor for the SMP EPS, you can find that relatively vibrating MBR has much lower of that. All right, so that contributes significantly, induce less fouling compared to the bar scouring anaerobic MBR. Now, when we look at the energy efficiency, okay, we compute, all right, and look at specific energy in terms of kilowatt hour per day, but this is from the lab scale study. You can see that the bar sparging increased significantly, okay, or vibrating anaerobic MBR save over 80 to 94% of specific energy demand. All right.
Sorry, Professor
And
Young. Sorry
yeah.
to disturb you in between.
Yeah.
We are running short of time. Would you please cut
Okay,
short your presentation.
finish it.
Yeah,
All right.
thank you.
So you can see that when we look at the overall energy consumption, you can see that there's a great potential for the vibrating environment MBR to achieve in terms of the energy recovery and also greenhouse in terms of greenhouse energy warming global energy equivalent. All right. So with that, I think thank you very much for your attention. Yeah.
Young, for your presentation. So we will straight away move to our next presentation. Now we will start with the short oral presentations for this session. And the first short oral presentation is SO3, and it is by Dr. Dillirani Nagarajan from from Taiwan. So she is here with us right now. So over to you.
Hello. Good afternoon, everyone. I welcome you all to this short oral presentation I'm Dr. Dillirani Nagarajan. I work with Professor Joshu Chang at National Cheng Kung University, Taiwan. Today, I'll be giving a very brief talk about the potential of macroalgae or seaweeds as a fermentation feedstock for the production of biofuels and various biochemicals. A very brief introduction about macroalgae, then I'll move about macroalgae-based biohydrogen production, and then I'll follow it up with macroalgae-based lactic acid production, and I'll conclude with the conclusions of the study and present some future perspectives. So macroalgae, or we all commonly know it as seaweeds or aquatic plants, which you can generally see in any seashore when you visit the beaches. But what we don't know about macroalgae is that they are a very rich source of carbohydrates, which can be fermented to various beneficial products. Now, why carbohydrates are present in many resources? So why macroalgae are important? And there are two main reasons for that. Macroalgae cultivation is an important part of maritime aquaculture production globally. So as of 2021, we have 30 million tons annual production of macroalgae, most of which are two types of macroalgae, red and brown, which are cultivated for food and hydrocolloid production. And because there's already a booming industry of macroalgae, it is very easy to procure. And the second important reason is that macroalgae have very low lignin content, 3 to 7%, but other lignocellulosic biomass such as wood and so on contain a very high lignin content of 25 to 30%. Lignin is recalcitrant, it's very difficult in pre-treatment and hydrolysis, so this is a very good resource. And currently major interest in macroalgae, the three different macroalgae are green macroalgae, red, and the third one is brown macroalgae. So I'll use this mouse. We have starch in green macroalgae which can be easily fermented, but when it comes to red and brown macroalgae, we have other polysaccharides such as agar and carrageenan which needs to be hydrolyzed, and in brown macroalgae the major polysaccharides are laminarin. So of these polysaccharides, agar, carrageenan and alginates are hydrocolloids in the food industry. There is an increasing interest in fucoxanthin because of its biological properties. And then there is phycoerythrin and phycocyanin utilized in the food industry for coloring purposes. So these are the component sugars. This is important because these sugars will be converted by the fermenting microorganisms into the valuable bioproducts. First, we'll talk about biohydrogen. So carbon emission is a major problem of the current society, and biohydrogen is a carbon zero fuel. But the major problem in biohydrogen production is that the current process is highly energy intensive, and the carbon emissions from biohydrogen production are way too high to be considered as carbon neutral fuel. So we need fermentation derived biohydrogen for biofuel purposes. So in this study, we utilized the green macroalgae, ulva, for biohydrogen fermentation. We hydrolyzed it with sulfuric acid. We used 4% sulfuric acid, and these sugars were derived: rhamnose, xylose, glucose, mannose, and uronic acid. We utilized it in dark fermentation with the anaerobic bacterium Clostridium butyricum, and we conducted both batch fermentation and continuous fermentation. continuous fermentation increased the yield of hydrogen from the macroalgal hydrolysate. We got about 1.3 moles hydrogen per mole reduced in sugar in batch, whereas we got 1.52 moles per hydrogen per mole reducing sugar in continuous fermentation. This is important because the maximum yield in mesophilic hydrogen fermentation is 2 moles of hydrogen per moles reducing sugar. So we got a very good yield. A small comparison of our study with the previously reported studies with similar pre-treatment strategies. Here it's very clear that we are getting very good hydrogen productivity, and the hydrogen content is always stable at about 50%, and we have sustainable yields about 1.4 moles of hydrogen per moles of reducing sugar. We published this study in Applied Energy in 2020. Next we move on to lactic acid. Now lactic acid is one of the crucial biochemicals in the market. It means it is a chemical which is derived from biological fermentation. Why there is a need for bio-based lactic acid in the market? Because lactic acid today is mainly applied in the production of polylactide, which is a biodegradable plastic. So for the production of polylactide, we need enantiomerically pure, that is either D+ or L- lactic acid. If we derive lactic acid from chemical synthesis, we cannot obtain any pure lactic acid. So bacterial fermentation is the way to go. But as with other bacterial fermentations, there are other challenges such as the feedstock cost and purification challenges. So here we are trying to use various types of macroalgal biomass as the source for lactic acid fermentation. We have used one representative macroalgae from each group. So we have used Ulva species for green macroalgae, which has a 50% carbohydrate content. We have used Gracilaria species for red macroalgae and Sargassum species for brown macroalgae. This is the fermentation process, and we used optimal strains for the fermentation of every macroalgal resource. And the main point I would like you to note here is the co-utilization of all the seaweed-derived sugars by the fermentating bacterium. When you take any renewable resource, the major problem is the underutilization of the different sugars, because there is always a mixture of sugars. It is not pure sugar, simply glucose or simply sucrose. It is a mixture of hexoses and pentoses. There's always a hierarchy that hexose is utilized first or a pentose is utilized first. So in this system, it is very evident that all the hexoses and pentoses are utilized simultaneously without any delay, and the entire fermentation could be completed in 24 hours with over 90% sugar utilization. So we used acid hydrolysis for sugar recovery from the biomass, and this is sugar recovery, sugar extraction efficiency from the different macroalgae. Red algae obviously resulted in the highest reducing sugar efficiency, and we used different optimized bacteria for lactic acid production. Green algae gave the highest productivity. That's because Ulva hydrolysate was rich in rhamnose, and we utilized Lactobacillus rhamnosus, so it attained the highest yield. And red algae resulted in the highest yield because galactose is always efficiently fermented by Lactobacillus. And for the first time, we reported fucose utilization and lactic acid conversion by Lactobacillus plantarum. And the yields were consistently high with 0.8 gram lactic acid per gram sugar. And to conclude this talk, I'd like to present two major points. One, macroalgae can potentially replace lignocellulosic biomass for two reasons. The product yield from macroalgae is very comparable to lignocellulosic biomass, and two, the cost of procurement and pre-treatment is very less than lignocellulosic biomass. And number two, as for the cost of procurement, we can easily obtain macroalgal biomass from two inexpensive resources, from the hydrocolloids industry, where they discard about 70% of the biomass, which is very rich in carbohydrates. And the second resource is a pelagic biomass, which can be collected on shores, which has to be disposed, but in lactic acid fermentation, we can find a very beneficial way. Last but not the least, I'd like to thank Professor Joshu Chang for helping me in conducting this research in his laboratory and for the resources, and Professor Dujong Lee for all his support during my research career, and the master students who effectively carried out all the experiments, Atika Nandini, Vinny, and Naomi. Thank you.
Thank you, Dr. Nagarajan. Any questions?
Hello. It was a good presentation. I have a question. The lactic acid you obtained was optically pure or a mixture of isomers?
It was a mixture of isomers. It was not very pure. We had at least 60-70% of D plus and different L minus. We did not focus on that. Our focus was to effectively utilize all the sugars present in the medium. But there are strains which can produce optically pure lactic acid. So we'll try, in future work, we'll try with that.
Okay, thank you. So we will move to the next short order presentation by Kuan Ting Lee from Taiwan. Please.
Okay, hello everyone. I'm Guantin Li, postdoc researcher from National Cheng Kung University. It's great to be here to share my recent study. The title is Caloric Value Upgraded of Lipid Containing Spankovigram by torrefaction for biochar with carbon neutral. This content focuses on the caloric value effect of different pyrolysis temperatures on the lipid contained in spankovigram. We found out the torrefaction to be a potential method to produce biochar with high caloric value by maximizing lipid retaining in biomass. Why is the spankovigram? Because it is a typical lipid-containing biomass and it can be reused as a promising solid recovery fuel. SRF is currently a hot topic to replace traditional fossil fuel. Reducing the use of fossil fuel is a key strategy to reduce carbon fee and increase the carbon rise. So how to reduce the carbon fee and obtain carbon rise at the same time? Using SRF is a definitely potential candidate, in particular lipid-containing biomass like spankovigram. Torrefaction is a way of carbonizing to maximize the retain of the lipid in biomass. And the torrefaction is defined as the carbonization of biomass under anaerobic condition at 200 to 300 degrees. And in general, spankovigram contain about 10 to 20% lipid. And we found the caloric value of spankovigram after torrefaction is 35% higher than that before torrefaction. And its lipid content is still retaining at about 11%. Since torrefied spankovigram has well hydrophobicity, low hygroscopicity, and low water activity, resulting it has great storage properties for solid fuel application. The amount of lipid in spankovigram later can be leached, decreased with increasing the pyrolysis temperature and the time. Spankovigram can extract about 10.28% of lipid, and while 200 TSCG can extract nearly 15%. which is mainly due to the contribution of the easy leaching of a lipid after heating the molecular chain. Okay, we can find it here. Oh, sorry, it's fine. And 300 degree is crucial temperature for retaining lipid molecule, and it can extract about 11% of the lipid. Saturated and unsaturated fatty acid are the main component of residual in spent coffee ground, including the palmitic acid, linoleic acid, and oleic acid, etc. The HHV of TSCG is proportional to the pyrolysis temperature, while the contribution of a lipid to a higher heating volume decreases the pyrolysis temperature increasing. The lipid content, the lipid amount of spent coffee ground contributes to higher heating volume by about 33.36%. And the contribution of the lipid content for 300 TSCG to caloric volume is still about 14.69%. After 300 degree, there is almost no lipid in the spent coffee ground, and its caloric value contributes to is almost entirely from the carbonylation level of the biochar. So my conclusion is torrefaction is a promising low-temperature pyrolysis technology for producing biochar from lipid-containing biomass. We always promote the torrefaction. And spent coffee ground have a rich lipid content of approximately 10 to 21%. The rich lipid content of the biochar decreases with increased pyrolysis temperature. So 300 degree is important temperature. Can retain the lipid content in biomass. And at the 300 degree, the lipid content decreases with pyrolysis time, and the highest lipid content was about 11%. So this yield of the highest HHV about the 28.60 megajoule per kilogram, of which a lipid contribution about 14%, while the carbonylation contributes to 85%. So it's calculated that each 1% lipid content of biochar contributes to 0.37 376 megajoule per kilogram. So overall torrefaction shows the developing potential for solid fuel production from the lipid content biomass, also which could be used as potential solid fuel to approach carbon neutral. So that's it.
Thank you so much for your presentation. We are ready to take any questions. Okay, if there are any questions, then we'll move forward to the next presentation.
Thank you.
And it is coded as SO9, and the presentation is from Professor Chia Hung Kuo from NKUST Taiwan.
Dr. Sharma, Professor, lady and gentlemen, good afternoon. I am CH from Department of Seafood Science, National Kaohsiung University of Science and Technology. I am very honored to give this speech at IBA-IFIB conference today. My presentation title is Green Extraction and Purification of Changjiu sulfate from jumbo square cartridge using a novel procedure combined with N9, ultrasound, and hollow fiber dialysis. Changjiu sulfate is an acidic carbohydrate belongs to glycosaminoglycans. The structure is composed by disaccharide. One is acetylgalactosamine and one is glucuronic acid. And there are 4 positions can be sufficient. So the Changzhou sulfate have a different type for A, B, C, D, E type. Changzhou sulfate can be used as a dietary supplement to protect joints, and it is now sold in market as a health food. It is also popular in many countries, including United States, Australia, Japan, and even in Taiwan. And now the Changzhou sulfate most is come from shark cartilage. So in this study, we developed a new source from jumbo square cartilage. Jumbo square cartilage is a waste from is a processing waste, and with a low commercial value. So if we take this material to extract Changzhou sulfate, can increase this product value. In the cartilage, Changzhou sulfate present in the form of proteoglycan. It means the Changzhou sulfate is linked with protein. So we use a process called protease-assisted iteration. And in this iteration, we added the protease to cleavage the protein, so the Changzhou sulfate can be released. And in the other hand, ultrasound-assisted iteration can cause cavitation and the general energy. The ultrasound can increase the iteration yield and decrease the iteration time. So we combine these 2 processes to develop a process called ultrasound-assisted enzymatic iteration. In our experimental flow chart, first we use the square cartilage sludge and added the acrylates. Then we put it into the ultrasonic base to iteration the crude Changzhou sulfate. Then we use a hollow fiber dialyzer to flush the crude Changzhou sulfate with 3 times of 3 times volume of water to flush out the protein hydrolyzed and obtain purified Changzhou sulfate, and the powder can be obtained after freezing dry. So in first we test the 3 kinds of protease, including papain, acrylates, and the protein NY, and we found the acrylates have a better iteration result. And then we also check the effect of ultrasound. The results show the ultrasound-assisted enzymatic iteration can increase 1.34 iteration yield as compared to the traditional sugar iteration. And so we use 5 labels, 4-factor central composite experimental design to build a response surface methodology. In this design, we need to run a 27 experiment, and we choose 4 factors, including iteration temperature, time, and the NI concentration and the pH. So in the table, that's the experimental range, and we get the Changzhou sulfate iteration concentration in the solution. So we use the experimental result. We can build a mathematical model in the below. This mathematical model we can use to draw the response surface plot. So when the iteration condition fixed at accuracy of 3% and the iteration time of 25 minutes, the relationship between pH and the iteration temperature can see in the response surface plot. So we can see the iteration temperature is an important factor in this process. Later, we use a technique ridge analysis to obtain optimal condition for extraction of chondroitin sulfate. And when the cordial radius of 1, the condition is temperature of 59 and the extraction time of 24 minutes, and amount of 3.6 and the pH of 8.25, we can get the maximum concentration of 11.9 milligram per milliliter. So the crude chondroitin sulfate, we have a choice to measure two purification. One is ethanol precipitation. One uses the hollow fiber dialyzer to flush out the protein hydrolyzate. The better result is use 50% ethanol to precipitate the chondroitin sulfate, can get the 77% of purity. And but the HFD gave a better result. We can obtain 85% purity, and we can see the purified chondroitin sulfate has higher content of uronic acid and the sulfate content. And so later we check the molecular weight, use the GPC. The purified chondroitin sulfate has a molecular weight of 200 kilodalton. And the structural feature was verified by FTIR. The blue line is chondroitin sulfate standard, and the orange line is purified chondroitin sulfate. We can see they have a similar functional group, including hydroxy group, uronic group, sulfoxide group, and sulfate group. And later we use the carbon-13 NMR to check the structure of chondroitin sulfate. We can find the chondroitin sulfate was sufficient at acetic glycose amine at the carbon 4 and the carbon 6 position. So the conclusion, we developed a process called ultrasound assisted enzymatic extraction and optimization this process. And then we take two methods to purify the chondroitin sulfate, and the HFD shows a better result to get 85% purity. The purified structure was confirmed by FTIR and the NNR, which is belong to chondroitin sulfate E form. So we have a new source to replace the shark cartridge chondroitin sulfate, use the jumbo square cartridge. And finally, thank you for your listening. I would like to thank most of Taiwan to support this work. Without our most of Taiwan support, I cannot finish this work. And thanks my students for completing this work. And I am also currently as a guest editor in sustainability and catalysis. Here is the title: Food Processing Technology Application for Health and Safety. And one is NI in medical, cosmetical, and food application. If you have any related paper, are also welcome to submit to this special issue. Thank you for your listening.
Thank you, Professor, for your wonderful talk. So we are moving to next oral presentation by Sofia Maria Ioannidou from Greece. She will be presenting her talk in online. So please. Sophia.
Can you hear me?
Yeah.
Yes.
Can you please share
hello
your
from
screen?
Greece. Yes. Let me share my screen. Can you see it?
No, not yet. Okay.
What about now?
Yeah. You can move to presentation mode. Okay, thank you.
Yes. We're okay. Yes. So, hello everyone, my name is Sofia Maria Ioannidou. I'm a chemical engineer doing my PhD in the Agricultural University of Athens, and today I'm giving a presentation entitled Sustainability Assessment of Polybutylene Succinate Production from Wheat Straw. Wheat straw is the stock left over after wheat grain harvest, while traditionally it has been treated as a waste. The valorization of wheat straw for bioprocessing and biorefinery development could be a good alternative as its composition in cellulose and hemicellulose offers a great potential for sugar-rich hydrolysate production and valorization for fermentative production of bio-based products and polymers. Polybutylene succinate is a bio-based biodegradable aliphatic polymer with interesting industrial applications as its mechanical properties are similar to those of popular conventional fossil polymers such as polystyrene. In this study, the three different stages for the pretreatment for the PBS production are taken into account. In the pretreatment stage of wheat straw, the feedstock is mixed with saturated steam to break the fibers of the lignocellulosic material, and an enzymatic hydrolysis process takes place using a commercial enzyme cocktail to make possible to mainly obtain glucose and xylose with hydrolysis conversion yield of 85%. In the monomers production phase, the sugar-rich hydrolysate is utilized for the fermentative production of succinic acid and 1,4-butanediol. For both monomers, the design of fermentation process is performed using literature data and includes a sterilization system and a bioreactor. After the production of monomers, different separation and purification technologies are implemented to obtain the desired products. The final step of the production is the PBS formation. Butanediol and succinic acid are mixed and the liquid outflow enters the esterification reactor. Subsequently, the polymerization of ester occurs as a polycondensation reaction in the presence of a catalyst. All simulations have been performed in the Unisim Honeywell software. After the design of the different processes presented, the material and energy balances inventory is developed. Next, equipment sizing takes place, the purchase cost is calculated, and all prices are converted to today's values. Finally, after further economic analysis, important economic indicators are estimated. As we can see, the indicators of the fixed capital investment and the cost of manufacture per kilogram of PBS are presented at different plant capacities to assess the effect of economies of scale and identify the plant capacity where a plateau has been reached. All indicators remain constant when a plateau capacity equal to 59 kilotons per year is achieved. In the table in our left, we can see the economic indicators in the optimum plant capacity for the evaluation of both feedstocks. The lowest cost of manufacture occurs at $2.63 per kilogram in the case of wheat straw, while the minimum selling price is equal to $3.27 per kilogram and the discount payback period equal to 7 years in this capacity. We can observe that although the cost of manufacture is almost the same for both feedstocks, the economic performance when glucose is used for PBS is better. The final economic indicator that should be discussed is the minimum fixture requirements, which is equal to 302.6 kilotons per year. Minimum fixture requirements can also be associated with the availability of the feedstock in the different geographic regions. The map of the slide has been created based on FAUST data. France, Ukraine, and Germany are the predominant countries, while in the second table we can see the ratio of the minimum feedstock requirements to the available quantities in each country. The next step for the assessment was the estimation of the environmental footprint of our process. This work is a cradle-to-gate assessment, and the boundaries includes the three stages of the production. The selected functional unit is output-based, so the final impacts are expressed per 1 kilogram of PBS using the CML methodology. The Gabi software has been used to estimate the two typical environmental indicators, namely global warming potential and abiotic depletion fossil. The global warming of our process is minus 2.88 kilograms of carbon dioxide equivalents per kilogram of PBS. The contributor for this negative impact is the agricultural phase of waste straw, while the production processes of the monomers contributes equally to the final total impact. The abiotic depletion of depletion fossil potential for the whole production process is equal to 62 megajoules per kilogram of PBS, while the wheat straw pre-treatment stage in this case affects the most the overall value due to the steam explosion selection as pre-treatment method. After the techno-economic and the environmental assessment of the whole process, a combined assessment is performed under the cost of externalities perspective. The main steps for the implementation of externalities include the definition of the activity, the estimation of the environmental impact as a physical parameter, and the corresponding monetization of this impact, while the monetary values has been proposed by the CE Delft. The cost of externalities is estimated for PBS production and is illustrated in the blue arrows. When the minimum selling price presented in the economic evaluation and the total externality cost are combined, the life cycle cost of PBS is estimated. Although the minimum selling price when glucose employed was 20 cents lower than the corresponding of wheat straw, life cycle cost of PBS from wheat straw is lower than the one with glucose employment due to higher externalities cost when the environmental assessment is considered in monetary terms. So to conclude, the wheat straw is a promising feedstock for bioprocessing development, while life cycle costing could lead to better comparison of different feedstock and technologies. And as future work, a biorefinery-based scenario and the consideration of the end-of-life stage of the polymer will provide a more holistic sustainability assessment. Thank you for your attention.
Thank you, Sophia, for your presentation. So, if there are any questions, we can take. Okay, so if there are any not any more questions, then we'll move forward to our next presentation. It is a pre-recorded one, and it's from Mirva, and we will. It's coded as SO15, so we will start with this presentation.
Hello everyone, my name is Mirva Serafidou and I'm a PhD candidate at Agricultural University of Athens, Greece. Today I will present you my work entitled Bacterial Nanocellulose Production from Different Crude Renewable Resources. At the beginning I will present you the composition of some raw materials, then the in situ production of crude enzymes by salt-side fermentation, the bacterial cellulose production via fermentation, and finally the bacterial nanocellulose production via acid hydrolysis. Bacterial cellulose is a linear homopolysaccharide consist of beta-deglycopyranose units linked together by beta 1.4 glycosidic bonds. Compared to plant cellulose, bacterial cellulose has higher crystallinity index, modulus of elasticity, and tensile strength. Also, it can be produced from crude renewable resources via fermentation. The conversion of bacterial cellulose into bacterial nanocellulose can be conducted through acid hydrolysis. There are many applications of bacterial cellulose in biomedicine, food industry, and packaging. In this slide, you can see the composition of the different feedstocks that we are working on for bacterial cellulose production. In the present work, I will present you the sugar beet pulp as a case study. Sugar beet pulp, after sugars and pectin extraction through biorefinery development, together with sunflower meal, were used as a substrate for aspergillus avamore growth in order to produce crude enzymes. Two moisture content were studied, 60 and 65%. As you can see on the right, phytase, protease, xylanase and CMC were produced with maximum enzymatic activity of 131, 12, 4.5 and 1 units per gram. These enzymes were used for hydrolysis of sugar beet pulp in order to be produced a sugar-rich hydrolysate. After 43 hours of hydrolysis, the final sugars were approximately 45 grams per liter. The hydrolysate was used for microbial fermentation for the production of bacterial cellulose. 4 grams per liter of bacterial cellulose was produced, with yield and productivity of 0.2 and 0.3 grams per gram and gram per liter per day. In order to convert bacterial cellulose into nanocellulose structures, acid hydrolysis was performed using concentrated sulfuric acid. More specifically, bacterial cellulose was purified and freeze-dried. Acid hydrolysis was followed by 50% sulfuric acid at 55 Celsius degrees, and after 32 hours, bleaching step was held by hydrogen peroxide. Ultrasonication and neutralization step was followed, using dialysis membranes to remove the external acid. Finally, bacterial nanocellulose structures were analyzed and characterized. Fourier transform infrared spectroscopy analyses were performed in order to examine the structural changes that occurred in the samples before and after acid treatment. All samples presented an absorbance band at 3,340 cm corresponds to the presence of hydroxyl groups, and absorbance at 1,050 cm, which is related to the beta-glycosidic linkage between beta-deglycopyranosis and cellulose. The X-ray diffraction technique was employed in order to determine the crystallinity index and crystallite size of the bacterial cellulose samples. The X-ray diffraction pattern of bacterial nanocellulose exhibited three characteristic diffraction peaks of 14.8, 16.9 and 22.7, which normally indicating the presence of both IA and IB crystal cellulose. The crystallinity index of bacterial nanocellulose was higher than bacterial cellulose at around 92%, whereas bacterial cellulose crystallinity index was determined 82%. Dynamic light scattering experiment of bacterial nanocellulose was performed in order to determine the size of the particles. The freeze-to-correlation functions were analyzed by the content algorithm to extract the distribution and relaxation rates. The hydrodynamic gradient distributions of bacterial nanocellulose particles were determined 72 and 931 nanometers. Zeta potential was determined as it is a critical parameter to evaluate the dispersion of the samples. You can notice that as the hydrolysis time increases, the absolute value of zeta potential increases too, gives better colloidal dispersion. Both acid-treated samples dispersed in the water and form homogeneous dispersion. Thermogravimetric analysis was also evaluated for identification of degradation temperature. In this case, as the hydrolysis time increased, the degradation temperature decreased from 338 to less than 300 degrees Celsius. The morphological characteristics of the final product were studied with scanning electron microscopy. On the left, you can see the structure of bacterial cellulose before the hydrolysis, and on the right, the bacterial nanocellulose after 32 hours of acid hydrolysis. The length of nanocellulose was a few micrometers when the dimension was approximately 46 to 73 nanometers. The ratio of length to dimension is a critical measurement in order to determine its suitability as a reinforcing agent in polymer matrices. In this study, the ratio was more than 13, high enough to be used for that kind of applications. To conclude, a sugar-rich hydrolysate was produced with a concentration of 45 grams per liter total sugars using crude enzymes from Aspergillus evamore. Bacterial cellulose was produced at 4 grams per liter. Bacterial cellulose can be hydrolyzed using 50% sulfuric acid, and finally the characteristics of bacterial nanocellulose indicate that can be used as a reinforcing agent in polymer matrices. Thank you for your attention.
So thank you, Mirva. Now we are going to SO18, Panayota Karanicola from Cyprus. She will be presenting online.
Oh, can you hear me?
Yeah, sure. You can share your screen.
You see it now?
Yeah.
Well, hello from Cyprus. I'm Panayota Karanicola, and I'm a PhD candidate at Cyprus University of Technology. My research focuses on the valorization of citrus processing waste for manufacture of high added value commodities through an integrated biorefinery approach. This project is funded by the Cyprus Research Innovation Foundation. The worldwide production of citrus fruits accounts for 143 million tons per year, resulting in industrial generation of 24 million tons per year of citrus peel waste. For a ton of processed fruit, up to 17 cubic meters of wastewater are generated and are generated through juice concentration, factory cleaning, and essential oils extraction process. How is this wastewater from essential oils extraction process is produced? Well, while the fruit is squeezed, fresh water passes through the extractor, holding back any remaining oils from the blades of the extractor. This water is mixed with the pulp of the fruit and centrifuged, isolating the essential oils. The remaining emulsion constitutes this wastewater. The main purpose of this work is the design of a biorefinery for manufacture of carotenoids, polyphenols, and bacterial cellulose using citrus processing wastewater. Different organic solvents for carotenoids extraction will be examined, as well as different adsorption materials for polyphenols recovery. The remaining wastewater will be applied for bacterial cellulose production. This study, the wastewater discarded from essential oils extraction process will be used, which is characterized by high organic value and is consisted of sugars, nitrogen, organic acids, essential oils, and polyphenols. The wastewater used in this study was consisted of 48 grams per liter of sugars, 1.1 grams per liter of polyphenols, and 6.7% of solids. The wastewater will be valorized through the proposed biorefinery. Initially filtered, and the solid fraction is used for carotenoids production, while the liquid fraction passes through an adsorption material for polyphenols recovery, and then is used for bacterial cellulose production. For the extraction of carotenoids, different organic solvents were used, showing that ethanol, the mixture of ethanol, acetic acid, and limonene, as well as the mixture of acetic acid and limonene, yielded the highest amount of carotenoids. Due to the cost of the different solvents, ethanol was chosen here. For the recovery of polyphenols, different adsorption materials were examined, including commercial resins, as well as biochar and activated biochar. The capacity of each material was examined by experiment at different concentrations of the material in the wastewater, observing that XAD 16N and PAD 900 have the highest adsorption capacity, while XAD 7HP and PAD 900 absorb the highest amount of saccharides. The desorption ability of each material is not three different flow rates at different volumes of ethanol. It can be observed that the rings in 16N have exhibited the highest desorption ability.
Miss Cranicola,
Comparing
your
combining
voice,
the desorption material.
yeah, your voice is breaking
Yes.
from your end. We cannot hear you properly. Yeah.
Can you hear me now?
Yeah. Carry on. Yeah, you may proceed. You may proceed.
Combining the results from absorption experiment with desorption experiments, we are choosing SAD16N as the suitable resin for this wastewater. Continuous experiments were performed using SAD16N. Flow RV of citrus processing wastewater were used in 1 RV of resin, absorbing almost the 72% of polyphenols and 3% of sugars. The resin is then rinsed with water in order to remove any impurities from the wastewater. The ethanol achieved 94% of desorption. An overall recovery of 64% was achieved. The wastewater resulting from the absorption was used for bacterial cellulose production using Comodobacter surcofermentans.
Miss Cranicola, sorry to interrupt you because we cannot hear you properly. I think there is some internet issue from your end. And yeah, please make sure internet connection is good. Can you hear us?
Can hear you. Can you hear me?
Yeah, we can hear you. You can just finish your presentation.
Yep. Summary, 1 liter of wastewater can result in the manufacture of 9 milligrams of carotenoids, 0.7 grams of polyphenols, and 5.3 grams of bacterial cellulose. The future work, different organic solvents for polyphenols desorption will be examined. The bacterial fermentations will be optimized, examining different nitrogen sources and upscaling in a bioreactor. Thank you for your attention.
Cranicola, for your presentation. So if there are any questions from the audience, we can take that. Okay, so we have one question.
Hello, Miss Karanicola. The work was really good. I have a question. The limonene that you are using for extraction, that you taken out from the orange peel, or you add a synthetic one?
As an initial step, we used a commercial one, but we are planning to explore the essential oils isolating from the fruit in order to recycle this.
Okay, thank you.
Thank you.
So we are moving to the next talk, SO21 by Chrysanthi Agreti from Greece. She will be presenting online. So Miss Argeti, over to you.
Hear me?
Yeah. Your voice is less. Please share your screen.
Okay. Okay, can you see my presentation?
As of now, but you can also switch on your video mode so that we could see you.
Yes, sure. So can you see my presentation or not yet?
As of now, but we can see you. Yeah.
Now?
It's loading, I think. Yeah, we can see it now. You can start. Yeah.
Okay. So hello everyone. My name is Chrysanthi Argiti and I'm a PhD student in Agricultural University of Athens in the Laboratory of Food Process Engineering. Today I would like to present you my work, which focuses on the valorization of brew spent grains by a non-thermal plasma treatment for the production of poly-3-hydroxybutyrate. In this study, brew spent grains, or BSG, which is the main byproduct from brewing industry, was used as feedstock for the production of poly-3-hydroxybutyrate, or PHB. Initially, 3 different pretreatment methods of BSG were evaluated: alkaline, hydrothermal, and plasma treatment. After the pretreatment follows the enzymatic hydrolysis of the residual solid in order to produce fermentable sugars. The hydrolysate of BSG after plasma pretreatment was subsequently used as a substrate to produce PHB via bacterial fermentation. The fermentation was conducted as a fed batch fermentation in a 2-liter bioreactor with a bacteria strain Parabucoteria saccari. The enzymatic hydrolysis of cellulose and hemicellulose results in the production of pentoses and hexoses, which could be bioconverted through microbial fermentation in several added value products. Non-thermal plasma, which is used in this work, is a novel technology for the efficient pretreatment of lignocellulosic biomass. Atmospheric pressure plasma is a source of highly reactive species, radicals, and ions. The ozone molecule typically generated in abundance in our plasma, and it can specifically attack the lignin of the treated material, leaving the cellulose and hemicellulose intact, maximizing the efficiency of enzymatic hydrolysis. Furthermore, it is an environmentally friendly and sustainable alternative to conventional thermochemical processes, as it deploys ambient temperature, atmospheric pressure, and dry gases instead of chemicals and solvents. Regarding the plasma pretreatment, we followed 2 strategies. At the first one, only the solids after plasma treatment was used for the hydrolysis step, and on the second one, the liquid and the solid after plasma treatment were combined. At the first set of experiments, 3 different voltage values and different pretreatment duration were evaluated. The initial solids concentration was 50 grams per liter, with a discharge frequency of 500 Hz and a duty cycle of 5%. The solids after plasma pretreatment were separated from the liquid by filtration and submitted to enzymatic hydrolysis. So the performance of the various pretreatment conditions of non-thermal plasma was evaluated considering both the overall conversion yield and the hydrolysis yield. The upper diagrams show the hydrolysis yield obtained considering the composition of glucan and hemicellulose contained in the pretreated with plasma solids, while diagrams below depicts the overall conversion yield, which was determined based on the composition of the solids before plasma treatment. In all cases, the hydrolysis yield of glucan increases as the pretreatment duration increases. A maximum yield of glucan obtained at 200 volt and 120 minutes per treatment, reaching up to 96%. Regarding the overall conversion yield of glucan, there are no significant differences, but a maximum yield observed at 200 volt for 1 hour per treatment. The pretreatment duration and the different voltage values doesn't seem to influence significant the overall and hydrolysis yield of both xylan and arabinon. Moreover, the highest xylan hydrolysis and overall yield was achieved at 200 volts, at 10 minutes in both cases. The next experiment was carried out increasing the discharge frequency at 1000 Hz, and 3 different duty cycles, 5, 10, and 15%, were evaluated. The result shows that the higher hydrolysis and overall yield of glucan was obtained with 10% duty cycle in both cases. In the case of xylan and arabinon, no significant differences are observed, but the highest hydrolysis and overall yield for both xylan and arabinon were observed at the experiments with 50% duty cycle. As you can see in the diagram in the middle, we use the solid and the liquid after plasma pretreatment, but with an initial solid concentration of 100 grams per liter. The glucan overall conversion yield was much higher than before, reaching up to 96% because of the exploitation both of dextrins and the cellulose that have been removed from the solid after the plasma treatment. The xylan and arabinon overall yield was around 30% in both cases. And finally, the results from plasma treatment were compared to alkaline and hydrothermal pretreatment. As you can see, two different temperatures were evaluated, combined with different sodium hydroxide concentrations. The diagram on the right shows that the highest overall conversion yield of both glucan and hemicellulose was obtained after non-thermal plasma treatment, reaching up to 96 and 40% respectively. Regarding the fermentation step, first, fed batch fermentation with stimulation of BSD hydrolysate with commercial sugars was conducted for the production of PHB. As you can see, cell growth was observed during the whole cultivation time. However, PHB accumulation was occurred around 15 hours and only after inorganic phosphorus was significantly low. The fermentation was completed in 33 hours of fermentation with a total dry cell weight of 140 grams per liter, and the PHB concentration was around 60 grams per liter. The yield of the fermentation was 0.34 grams per grams, and the productivity was 2.74 grams per liter per hour. The diagram in the middle shows the consumption rate of each sugar by the bacterial strain Parabulcoteria saccari. And it seems that it can consume xylan as well as glucan. So we carried out a second fermentation with BSD hydrolysate after plasma treatment as a carbon source and concentrate BSD hydrolysate as a feeding solution. Here we can see that the accumulation of PHB starts after the depletion of phosphorus at 15 hours. The fermentation in the case of the hydrolysate stops at 34 hours with a dry cell weight of 130 grams per liter. The PHB concentration was 71 grams per liter with a content of 55%. The yield of the process was 0.28 grams per grams and the productivity was 2.36 grams per liter per hour. To conclude, BSD seems to be a valuable carbon source and can be used for the production of PHB. The highest hydrolysis yield after non-thermal plasma was achieved at 200 volt for 30 minutes with a 10% duty cycle, with glucan and hemicellulose overall conversion yield 96% and 40% respectively. And finally, the fed batch fermentation with BSD hydrolysate resulted in the production of 122 grams per liter of total dry weight with a PHB content of 55%. Thank you for your attention.
Thank you, Ms. Agreti, for your presentation. So if there are any questions, we can take it now.
Hello, Ms. Agreti. I have two questions. So, on a high scale, what is the feasibility of using cold plasma in pre-treatment of biomass? And the next question is like, what is the cost analysis compared to the conventional pre-treatment methods?
Okay, so the scale up of the plasma process, it's more than possible because we only need a plastic reactor and the plasma probe. So it's very easy to construct one. Regarding the cost, we have during the process we have ambient temperature and atmospheric pressure. And we don't need any solvent. We use only dry gases such as air. So based on the literature, we see that the energy consumption is much lower than the conventional, compared to conventional methods. It's almost, if I remember well, almost 20 times lower. I don't know if I answered your question.
Yeah, sure. Thank you.
Thank you.
Thank you, Ms. Agreti. So with this, we come to conclusion of our final session of the day. So thank you all the audiences those who are present online as well as those who are present with us physically. So thank you all. And now after the completion, we move ahead with the tea and coffee. And after tea and coffee, we'll be having the gala dinner. And we'll be proceeding towards the gala dinner by buses towards the hotel. So thank you very much. And for tomorrow, we will start the session 4 from 8 a.m. in the morning, and it will start with the plenary lecture by Professor Jonathan W.C. Wong. So, and it will be followed by invited lectures as well as the short oral presentations. So we'll be having 4 sessions tomorrow. So it will be a stringent day for us tomorrow. So I request all of you to be there on time to join us for the session C as well as for session A and B. So I thank you all once again for being there with us. Thank you.